meeting is being recorded. Hello, Harmaz. Good morning. Sorry, good evening.
Hi, good morning, Raja. Can you hear me?
Yeah, I can hear you perfectly. I'm so excited to hear your presentation.
People in the room already?
Sorry?
Or the audience already in the room?
No, audience. Basically, what will happen is I presented actually, I had my tutorial in the previous one
Oh,
and
okay.
I presented something. So
Mhm,
basically, what they do is just 3-4 minutes before they connected to the room.
mhm.
And now, basically, what happened is we are supposed to give 3 hours tutorial before, and it went to like 3 hour 10 minutes with all Q&A. And they went for lunch. So I think they might be late 5 minutes. We still have 7 minutes. So that's my experience in the morning. So
Okay, okay. So
yeah.
they might be actually late quite a bit if they just.
No. I think it will be like they're trying their best to be on time. So
Oh, okay. So
yeah.
they had maybe 1 hour lunch and
Yeah,
they
exactly. So
now they
exactly.
got like 45
Exactly.
five
Here it,
minutes, something like that.
yeah,
Okay,
I'm sure they will be like they
okay.
will trying to
That should
correct
be
actually.
okay. Yeah.
Hi.
My colleagues from microchip are already there, maybe not in the room yet, but
Okay.
yeah,
I'm sure they look after the presentation. So are you
yeah.
from Bourne Bay? Like are you from Vancouver?
Yes,
Okay.
I'm from Vancouver, microchip, and I didn't get my visa on time. It was like a long process. I've been to
Okay.
India 3 times before on
Okay.
e-visa.
Yeah,
Right now,
yeah.
there was something happening between the two governments. They were not
No.
issuing
EVSI,
e-visas.
the EVSI is back actually.
Yeah,
I
too late for me, right?
okay. No, actually I
But
was there last month on e-visa only.
uh, I had my colleagues, they wanted to come to Vancouver. They were like about a month waiting.
Okay.
And on my side, I also waited for almost a month. And
Okay.
then I canceled my ticket. I had my ticket and everything.
Yeah.
I mean, I understand now e-visa is back in
Yeah, it's back actually.
2023.
It's back. You can, straight away
Yeah,
apply, get in minutes. It's like
yeah.
exactly how I apply visa to Canada, like online. It's so simple.
Yeah, there was something. I think it's
Yeah.
a diplomatic wrangling.
Yeah.
Something was happening between
Yeah.
two
How was
governments.
Vancouver? I haven't been to Vancouver since last year actually.
Okay. Oh,
Uh,
okay.
I used to work for a company called Infi, uh,
Infi.
Infi,
Okay.
and I used to come quite frequently to Vancouver actually.
Yeah. We
Now,
have our yeah. There's a small mixed signal office of Infi. I guess now Infi is acquired, but
Marvel,
still
yeah.
Marvel. Yeah.
Because of that question only, I've been let go. So otherwise, like I worked in
Mm,
N5 for. Harmuch, one more thing is, if you don't mind, can I ask you something?
sure.
I was like, is there a way you can share your slides with me? Like I presented early, like you can see my
Mhm.
name and all in the.
Yeah.
I presented a band gap tutorial actually, so
Mhm.
you can see who I am actually rather me anomalously asking. Is there a way you can uh, share slides with me after the presentation?
Okay, I'll check.
Yeah.
I don't know. It was approved for presentation, not distribution, but I'm sure I can share
Yeah.
it with you, and
Yeah.
in exchange I get your slides or something. So
Yeah,
so
I can do that.
that justifies it.
Yeah.
But
Definitely. After your presentation, I'll get in
yeah,
touch with you. And
yeah, sure.
mostly my tutorial is and like it's for senior people, I don't like it, but that's half of my thesis.
Okay.
Mostly how to check the startups, how to be careful with startups, and like
Yeah.
uh, like how to like if someone doesn't know band gap, how they come up with the band gap like from scratch, something like that.
Okay.
Anyhow, I
So
think
it's very
very
deep.
fundamental.
Fundamental. Yeah, that's good. And mine is mostly based on our own experience on clocking in the
That's good.
past 10, 15, 20 years. So it's not like a
Okay.
classic PLL
Yeah.
textbook
Okay.
tutorial,
Uh,
It's a little bit
Okay.
of, you know,
I
I
worked
try
very
not to
less.
show many formulas or anything. And just
Okay.
try to explain
Yeah.
concepts and our
Okay.
experience and
Okay.
results we got in different categories of
Yeah.
clocking.
See, just to interrupt you. So now they added cafeteria. That means people are in the, now we both will be moved to the room now.
Okay, that's good.
Thank you for the talk, Harmuch. Okay. Good luck with the
Thank you,
presentation.
Raja.
Bye. Bye.
Bye.
We'll start in 5 minutes or so.
Okay.
Okay, right?
Okay.
We'll start in 5 minutes. Hello, Harmos. You can hear us, right?
I can hear you.
Okay, great. Thank Rajshekhar, you can hear us.
Thank you. Yeah.
Okay. Harmos, how about yourself?
No, I told him 5 minutes. I think he probably
Hi, Ramos. Can you hear us?
Hi, Satish. Yes. Hello, everyone.
Okay. Yeah, you are still fresh.
Why is audio is coming less? We are not able to hear.
Can you go full audio, Ramos? Just checking if you can. You're coming out weaker.
Okay. Is the volume on Zoom or?
No, I think it's okay. Just maybe you have to speak up a little louder.
Okay.
This is perfect. Rajshekhar, when he's
Yeah.
talking, it is perfect.
Yeah.
Rajshekhar, can you speak once?
I can hear you.
Yeah.
Um,
his audio is coming.
How many rooms do we have there? I saw 2 rooms at some point.
No, it's just the front and back. Yeah, just single one. Yeah.
Okay.
Split view.
And we manage. Yeah. We'll start. I hope everybody has joined back. So good afternoon, everybody. Let's continue our second session. So our today's tutorial is on CMOS clocking technology for wireless and SoC applications. This tutorial will be presented by Harmos Jahanshai, who couldn't join us here because of some unforeseen situations, but he is present online for us. Okay. He'll be represented by Satish from Microchip here. Okay. So Dr. Harmos Jahanshai has received his BSc and MSc in Electronics Engineering from Amir Kabir University. He has received his PhD from University of Windsor in Analog VLSI and Neural Networks in 1997. And he was a postdoctoral fellow at the University of Toronto in 1997. He has worked on high-speed IOs and clocking circuitries then. Since 2000, he has been with the Mixed Signal Development Group at PMC Siraj, which was acquired by Microsemi in 2016 and Microchip Technology in 2018. He's currently an associate technical fellow at Microchip and has got 26 patents, 42 publications, and a variety of industry experience in designing and mentoring dozens of high-speed and high-performance clocking and analog designs. So he has also got experience in SerDes and wireless products. He's also a member of Royal Astronomical Society in Canada, and he spares his free time in watching the sky from his backyard through his 8-inch telescope. Welcome, Dr. Harmos. You can hear us, right, Harmos?
Yes, thank you for the nice introduction. You can hear me too?
Yes, we can.
Better now?
Correct.
Yeah.
Sorry for keeping you late. I know we know that it's very late there.
No, that's fine. I appreciate your attendance of the tutorial, everyone. I wanted to be in that room with you right now to present my material and interact with you in person. I even booked my ticket and everything, but unfortunately my visa application took too long. And I ran out of time after a month, in fact. I think this was a common situation between Canada and India towards the end of the last year. Hopefully it's being resolved in 2023, a little bit too late for this trip for me. Fortunately, we have this technology that all of us use on a daily basis to interact across the world. Many of you in the room probably contribute to this one way or another. I'm also glad that I have my colleagues in the room from Microchip's Bangalore office. If I need help during a presentation or answering any question, etc. Anyways, I'll stop here. I think maybe Satish has some material first, and I'll go next.
That's correct, Harmos. Yes, you can stop sharing. Satish will take it forward. Thanks, Harmos, for your intro. We hope we see you soon here again. Okay, I'll give it to Satish to take it over.
Hey, good afternoon, everyone. Okay, how was the lunch? It's that time of the day, right? You'll have to keep everyone energetic, and we'll try our best, but can't guarantee. It's up to you guys to show some interest as well, right? Before we get started with the real technical stuff, I thought, yeah, Harmos?
Sorry, I was just saying, don't tell me about lunch because I missed it.
Oh, yeah, you missed a great lunch. Yeah, we'll definitely, it's so nice next time you're here. Yeah. Okay, so before we get started, I thought it's important we tell our background, right? Like why we are presenting or why we are qualified in presenting all of this stuff, right? So there's quite a lot of valuable information that Harmos is going to present in the next few minutes, right? So you will see how all of that data was gathered, and it's all experience, right? And Harmos himself has worked more than close to 30 years into this stuff, clocking stuff, and there's quite a lot of wealth in the team and group and stuff. So I thought it's only appropriate we start with the brief intro and then move on to the other stuff. Okay, the minute microchip is pronounced, I think most of the people would probably relate it to microcontroller than any high-speed stuff, right, or high-end stuff. But microchip, by history, like it's been there for over 30 plus years, 8 billion plus revenue, 20,000 plus employees, and this is just a marketing slide here, right? And into multiple domains as such, like industrial, data center, or automotive, FPGA. For people in Hyderabad, the micro semi probably you will relate to as FPGA and other timing group and so on all that. But specifically where we come into is like we were originally PMC Sierra, for people who knew. Our group basically catered to the data center where you have generations of high-speed products, right? So that's where this clocking is also going to get fit in, right? So, okay, I don't know if there is a project pointer, it's going to work. Okay, it seems to be working. Okay, so the data center and communications is where we, PMC Sierra was acquired by Microsemi, and Microsemi to Microchip, we came in there, right? And specifically, our group is called Mixed Signal Development Group, AES, Advanced Engineering Services, Mixed Signal Development Group. Microchip India I think it's over 2 decades. It started out in Bangalore with acquisition of Microsemi, has also expanded into Chennai and Hyderabad, right? And then headquartered in Phoenix, Arizona. Again, as I said, Microsemi, PMC Sierra, all the history there. And our group basically has been there since years, transitioned into Microsemi and then Microchip now, right? So we have not been disintegrated or anything. We just got transformed from one company to the other, and we exist since the time PMC Sierra existed. So the group is intact, and MSDG, we call it as the Center of Excellence for delivering high-speed SerDes IPs related to all the SoC needs, PLLs, DDR5s, and all of the stuff. And we started designing, as you can see, starting from 1.2 down to 3 and 2 nanometers now, right? So, and we are currently only focused on DCS and CBU. That's the communications and data center products. That's where all of the high-end stuff that happens. And then the group has mix of all the analog, digital, RTL, ESD, SI packaging, and a lot of those expertise. And as I said, design centers in India at Bangalore, Chennai, and Hyderabad. Also, the team is spread across India, Canada, Malaysia, and US, right? And obviously, Hormuz is located in Canada, Vancouver. I think it's almost past his midnight, and it's almost 12:20 on Saturday. I mean, you can see the dedicated people like him making this group successful. And what is special about it is the team has developed differentiating IPs that help sell the product lines with these IPs in them, right? Okay, so briefly, just I won't spend too much time on this, but the product lines include, as I said, 2 BUs, business units, that's communication and the DCS, data center solutions. In communication business units, they are separated as different verticals, right? So you will see quite a lot of stuff, and the newest addition is basically the space computing, right? So if I look at it here, it's a new stuff which is only specifically built for NASA now, right? So a lot of microchip folks may be showing off with all this LinkedIn news article which says, okay, we are building a 64-bit controller, space computing controller for NASA. It's all coming from this one, right? So industry leader in OTN processors. And these devices are the ones which drive our need for high-speed SerDes itself, right? So you can see the Ethernet PHYs, which runs at 1.6, 1.2 Tbps here, right, throughput. And then you also have like Digi series, like Digi G5, which again calls for really, really high speed SerDes, PAM4, 112, looking at 224, a lot of those needs, right? So probably not many out in the India design development area working on these niche skill sets at all, right? So, and just quickly on the data center business unit, like we have 3 product verticals again. Storage, memory, and a lot of this. Again, it's all PCIe, SAS, SATA, you name it, you have everything there, right? So you have the IO controllers, radon controllers, SAS expanders, CXL, the new baby on the block, and then you have on the performance side, you have flash stick device, we call it. Like you have a laptop, you have a SSD, and then maybe 2 out of 3. Or out of 3, 2 SSD controllers might use PMC Sierra's legacy memory controllers on them, right? And then on memory infrastructure, these are the new ones that we are in, is basically the smart memory controller and the CXL based memory controllers, where it helps expand the memory without increasing your address capabilities and all that. So just to summarize, 20 plus generations of SerDes, right? We have a history of building 20 plus SerDes generations, starting from Gen 1. We are doing Gen 7 today, right? I mean, not many probably would be, again, I'm boasting, right? So, but forgive me, but that's definitely a proud thing to call out loud and say, hey, we're doing something really high speed. And then specifically on, if you look at this generations of clocking, that's where we are going to spend a lot of our time sharing our experience more than teaching somebody, just sharing our experience on how we did it, what are the techniques, how do we measure ourselves against competition. A lot of those things we'll be discussing in the next few minutes, right? So again, quite a lot of experience and wealth on clocking. Again, we have rest of the IPs and other stuff I'm not going to talk, but this at least gives you a fair understanding of maybe why we are qualified in talking about high-speed clocking, right? So just a last slide here is just a summary of the MSDG, whatever we talked about. We are basically, within the company, we are like an IP supplier to some of the business units, right? So we have a lot of hardened IPs that's up to even Gen 5 today available, siliconized. And then for the new college freshers or anyone, yeah, we do have like a lot of intern opportunities, 6 months to 1 month, 1 year. And then we also have like lateral openings and stuff. If anybody is interested, we'll drop the card here. You can obviously get connected with us and we can obviously take it forward, right? And also we are working with a lot of industry, like universities also in a collaboration opportunities and stuff. Yeah. I think I'll pause it here. There are no questions. I'll let Harmos take over and start the real show. Okay, before I hand off to Harmos, I really wanted to say that, I mean, to the VLSI organizing committee, it's a great opportunity given to us to showcase our experience and share our knowledge on this field, right? So thanks so much to all the organizers and specifically the Silicon Lab guys here giving us a space to do all of this stuff. Okay, one last thing. So I know this is post-lunch, Sunday afternoon. We'll try and wrap it up pretty quick, right? Like 3:30, maybe 4 o'clock, right? But just to make this more interesting, we'll have surprise trivia or a quiz at the end, right? So maybe 5 questions, and anyone who answers would definitely take home some goodies, okay? So take out your notebooks, pens, be ready. We'll try our best to keep you engaged and focused, but yeah. Definitely, okay, you're going home with some goodies, huh? Okay, Harmos, all yours.
Okay, thank you, Satish.
Yeah, we stopped sharing screen here. You should be able to share.
Okay.
We'll take a break at 3 p.m. Harmos. 1 hour, 10 minutes from here, okay?
Okay.
It's fine, right, for you? 1 hour, 10 minutes from now. We'll take a short break for 15 minutes then. Okay. Meanwhile, if anybody wants coffee and all right, it's always available. Thanks. You can go ahead.
Okay. Thank you, Satish, and thank you everyone again for the attendance. I'll go to the main slide presentation again for people who just got to the room. I wanted to be there with you, but my visa took too long and I ran out of time. So hopefully next time. So without further ado, I'll jump to the presentation agenda. I'm going to talk about CMOS clocking technology for wireline, wireless, and SoC applications. I'll start with an introduction. Let me see if I can get my laser pointer. Some background and terminology and definitions, for example, on clock jitter and phase noise and things. About 15 slides that we will need for the rest of the presentation. Then in the subsequent sections, I'll talk about CMOS clocking technology developed in our mixed signal group. And I'm going to give you a taste of clocking IPs that we have developed over the years and the type of applications that they support standards and rates, etc. I'll go through 4 categories listed here. These are different clocking IPs for different applications. The first one is for SerDes clock synthesizer PLLs for wireline standards. The next one is ultra low power, ultra low phase noise RF PLLs, also known as LOs or local oscillators. Then we'll talk about jitter cleanup PLLs and on-die clock distribution. And then digital PLL clock synthesizers for SOC, core clocking, and timing. And finally, a couple of slides on future developments and roadmap. I will stop my video because it's Saturday evening late and people in the neighborhood may be streaming movies. I don't want to get delay. I have just a couple of short GIFs and transition slides. I don't want to slow it down, but in QA time, again, we turn on camera, okay? So first, the introduction. As Satish also mentioned briefly, over the years, we have had at least 15 generations of clocking IPs across different technology nodes and architectures that support different applications and standards. I would categorize them into the 4 major groups that I mentioned. Now a little bit of more details, and then we go through each section with more details of what we have developed and performance, etc. So the first one is SerDes PLLs. These are high performance, low power fractional clock synthesizer units, or CSUs. Some people use the acronym CMU for clock multiplier unit. It's the same thing. Maybe clock synthesizer emphasizes a bit more on fractional nature of it, but it's just a terminology. These IPs and PLLs operate the ones that I guess is in our portfolio up to 16 gigahertz to support 32 gigabit per second NRZ wireline SerDes applications, and also 29 gigahertz, the more recent one that we are designing for 112 gig, in fact, up to 116 gigabit per second PAM4 applications. These are standards from OIF CEI and also IEEE Ethernet applications that is at 106 gigabit per second PAM4. So these clock synthesizers cover those standards. The second category is going to be ultra low phase noise RF PLLs. And these PLLs have even lower jitter than the first category. They serve as local oscillators or LOs for our RF transceiver products for wireless base station applications, things that you see on top of these towers. Here we require an absolutely low phase noise and jitter. So this is the prime target of these LOs. We don't have many of them on a die, maybe 1 or 2, not much more. As opposed to the first category, these SerDes PLLs, we may have more than 100 PLLs on the same die. So they need to be low power as well as high performance. But the second category, power takes a back seat, but the performance is much more demanding in terms of jitter and phase noise. The third category is the jitter cleanup PLLs, also known as jitter attenuators or JATs. These IPs generate a clean reference clock on die from a noisy external reference that we receive on board or from a noisy recovered data. And then we distribute the clean clock across a large die usually to get to these different PLLs and use it. The fourth category is the digital PLLs or digital clock synthesizer units. We call them DCSU. They are AD PLLs, all digital PLLs, and they are meant for generating system clock and timing for digital core on large SoCs. They are fairly versatile, feature-rich, and low power and area. We can drop them anywhere on the chip near a digital macro. They have no inductor or anything like that in them, so they are pretty small size and flexible in terms of placement. But they are not generally very required to be very high performance in terms of jitter. What matters for these PLLs, for these digital PLLs, is period jitter, not the long-term phase jitter that would matter to series PLLs or LOs. For all of our IPs, including blocking, also for other components of the SerDes, we define figure of merits or forms. And we track these forms over time to ensure we improve the form over time and remain best in class. Our PLLs are built in various CMOS technology nodes and foundries down to 16 nanometer and now 6 nanometer FinFET. Next year, this year actually, 2023, we'll start at 3 nanometer development. And these IPs, as I mentioned, support up to 112 gigabit per second data rate per lane. On a typical large SoC, we may have more than 100 of these PLLs. Therefore, power, noise coupling between PLLs, and a lot of issues like that exist that we need to manage. Over the time, we have developed a large portfolio with multiple PLL designs per node. So even in each technology node, we may have like more than one generation that we improve on the first generation or application or rate changes. We have, as far as I know, we have more than 35 patents in clocking alone. And I'm honored to have contributed to about 2/3 of these patents. We have 18 publications on clocking as well. We did not have a strong publication policy in the past. In fact, under PMCC era, we were not allowed to publish in general. They just wanted patents, but this is changing under a microchip. So we can, depending on the nature of the work, we can publish or we can patent. In fact, if you search VLSI, the VLSI conference, you'll probably find at least 2-3 papers and a couple of more presentations from microchip. I'll start with some basic definitions on jitter, because in different categories, I'm going to talk about different jitter components or terminologies. The first one is phase jitter. So the phase jitter is deviation of a signal or clock from its ideal position over many consecutive cycles. This definition actually applies to both clock and data. So in this picture here, in blue, you see the ideal clock or ideal location of the phases. And in red, you see an actual clock. So you see the edges are not in their ideal position. So the difference between actual location of the edge and the ideal location of the edge is the phase jitter. And other terminologies exist for the same concept, more or less. For example, TIE, time interval error, here shown is the phase jitter at this point in time. So if you take these numbers, you have basically a discrete sequence that tells you for each clock edge how much phase error or phase jitter you had. Other terminologies used that more or less have the same meaning are long-term jitter, edge jitter, or accumulated jitter, obviously because this kind of jitter accumulates over time. So if my actual period of the clock is a little bit smaller than the ideal period in the first cycle, I get a small error, and then it grows and accumulates over time. And if I have a phase modulation, low frequency, the same thing happens, and it comes back, and at some point I get to the ideal period of the clock, and then it continues in the opposite direction. In frequency domain, we talk about phase noise rather than phase jitter. So for phase noise, you can imagine the spectrum of the clock. And if the clock is jitter-free and ideal, you have all the energy concentrated at one frequency, the ideal frequency of oscillator, which is the ideal carrier. When you have a real clock, it has some unwanted phase modulation. So you will see skirts around that ideal carrier on the spectrum. So imagine you have an ideal filter with 1 Hertz bandwidth and a brick fall, and you sweep it across the spectrum, across the frequency, and you measure the energy in each bin. So this measured energy is the single sideband 1 Hertz power, right? And then you continue to do so. So the power of a single 1 Hertz sideband, not both sidebands, just one sideband, divided by the total power of signal is called phase noise. So if we plot this, measurement equipment usually measure this and display this as a single sideband phase noise, and the unit of it is dBc per Hertz, dB with respect to carrier, and per Hertz means just the density of the phase jitter that I mentioned. Then there's a relation between time domain and frequency domain of each signal. And in this case, if you're interested in phase jitter, you can take the integral of phase noise over a band, from F1 to F2. So you take basically a phase noise, you do 10 to the power of phase noise divided by 10. So it's basically converting from dB to linear scale. Then you integrate from F1 to F2. This is called jitter filter. Each standard defines a different jitter filter. Then you multiply it by 2, obviously because the real signal has 2 sidebands. And then you take a square root and you get radian RMS at this point, and you divide it by 2 pi FC, FC being the carrier frequency. So you get the RMS jitter in units of second. Okay. The lowest frequency here in the measurement in time domain corresponds to the window over which you measure the phase jitter. So you collect over, if you collect, for example, clock or data signals information over 1 microsecond, this is equivalent to 1 megahertz. So the lowest frequency that you can imagine in that clock is 1 megahertz. On the other hand, the highest possible frequency in theory in each clock, if the clock is frequency of clock is FC, the fastest phase modulation you can imagine on it is FC over 2. So that's sort of a Nyquist limit. So one cycle shrinks, one cycle expands. So the frequency of that kind of phase modulation is clock over 2. And if there's anything higher than that, if there's noise on power supply or anything, it gets sampled and folded down to below FC over 2. Again, different standards talk about different jitter filters to measure the clock jitter or data jitter for that matter. The next definition of jitter that you're interested in is period jitter, where I briefly mentioned that this matters more for the timing applications, STA and digital clocking of the core. So this period jitter is deviation of a signal period compared to the ideal period over a specified number of measured cycles. So this is useful in calculating timing margin in digital systems or static timing analysis. For example, data setup time, hold time violations, etc. It turns out that if you think about the definitions, period error becomes a discrete difference or derivative of a phase error time sequence. So we said each data we collect is actually a time sequence. So a discrete difference of phase error becomes period error. So what happens is this emphasizes high frequency, because whenever you take the derivative of something, it emphasizes high frequency. So period error is more affected by high frequency noise. The next definition is cycle-to-cycle error, or C2C. This is a variation in one cycle or period between adjacent clock cycles. So it's not compared to ideal period, it's just compared to last period. And it's kind of clear from definition that this one becomes discrete difference or derivative of period error. Okay, so in summary, here we have phase jitter, which is deviation from ideal edge. Then we have the period jitter, which is deviation from ideal period. And then we have cycle-to-cycle jitter, which is deviation from zero difference between two adjacent cycles, because that would be the ideal situation. A couple of examples here. I just put the basic definitions up here and color-coded the real measurements. So here we have a phase-modulated clock. The ideal timing is shown in dashed lines, orangey dashed lines, and up here the same color. And the modulated clock, a real clock, is shown in black. So the first tab of measurements we see here shows the period of the clock. So if you look at it carefully, you see in the first 4 cycles, if the clock period ideally was 1000 picosecond or 1 nanosecond, in the first 4 cycles or so have a smaller period. So let's say 990 picosecond. So that means we have a period error of minus 10 picosecond over 4 cycles. Then the period expands, and over 8 cycles, we have 1010 picoseconds. So it means a period error of 10 picoseconds. So these edges, when you look at the time interval error or phase jitter, in the first 4 cycles, you see it accumulates and goes down to minus 40 picosecond. And then over the next 8 cycles, it ramps up back to hit 0 picosecond and then plus 40 picosecond, and this situation repeats itself. So you see in this example, again, that you have a triangular waveform here for a TIE or phase jitter, and you have a sort of rectangular waveform for period jitter. So this one, period jitter, is derivative of a phase jitter again. And for cycle-to-cycle jitter, we only have 2 jumps when we went from minus 10 picosecond period jitter to plus 10 picosecond period jitter. So the period changed from 990 to 1010. So we have 20 picosecond cycle-to-cycle jitter in that moment. And then the next time when the opposite happened, we had minus 20 picosecond cycle-to-cycle jitter. So if you look at this waveform compared to the period jitter, the cycle-to-cycle is the derivative or discrete difference of period jitter. So this summarizes these 3 definitions. So I have a little bit of animation here. Do you see that? Is the speed enough to show the signal which is slowly being phase modulated? So here we have a clock signal with a significant low frequency phase jitter. So color-coded across y-axis is in blue is phase jitter. So you see it grows, to plus and minus. So we have fairly large phase jitter due to this low frequency jitter, because it accumulates this low frequency accumulates over time and it gives us a lot of phase jitter. But if you look at it carefully, the period of signal is not changing much, and the red line is more or less hovering around 0 in this direction. So through this example, we see that the low frequency noise is de-emphasized in period jitter. But for phase jitter, this low frequency actually accumulates a lot over time. And then we have another example here where you clearly see a faster phase modulation. So this clock is having high frequency jitter, and high frequency jitter creates both period modulation and phase modulation. So both phase jitter and period jitter are relatively large compared to the first example that we had a small period jitter. Different standards for wireline, telecom, datacom, and then wireless applications. We find different specifications for clock and data. So as we explained, real clocks have phase noise and jitter on it, and phase noise is expressed in units of dVc per hertz in frequency domain, and in time domain, we can measure it on oscilloscope, for example, and we talk about RMS jitter or peak-to-peak jitter. For example, here on an oscilloscope, we are zooming into a rising edge of a clock, and we are building a jitter histogram, which is really the distribution of these zero crossings. So this looks like some sort of Gaussian distribution. So most of the time, the edges hit zero line around here, right? And then occasionally, if you wait long enough, you will get this longer tail on this Gaussian histogram. So one, the RMS value, you can measure it from this kind of measurements, and depending on the depth of measurement or bit error rate, target bit error rate, so I'll explain how you calculate the peak-to-peak. And again, the relation between RMS phase jitter and the phase noise is shown here. And on this picture on the right, you see a typical phase noise in red. So low frequency, this could be from the reference clock flicker noise on a reference clock. And this shape could be from a PLL. I'll show you an example later. Then sometimes we have spurs, right, on the spectrum. And then you go to higher frequency, you hit some kind of noise floor. So you don't go lower than certain limits. So this is limited by noise floor of the system or performance of the VCO itself to some extent. So usually telecom applications care about low frequency phase noise and jitter. For example, from 10 kilohertz to 20 megahertz, or different standards in OTN, optical transport network. We have different jitter filters at higher rates, 80 kilohertz to 200 megahertz. But usually it's what we call more like in-band noise, low frequency integration, or narrow band. On the other hand, most of the wireline applications, other than this kind of OTN or legacy SONET applications, they care about broadband jitter. So we call this datacom. So in datacom, the integration limit of jitter or phase noise usually goes up to the Nyquist limit, which is clock over 2, and down to a fraction of baud rates. For example, a lot of standards for datacom specify baud rate over 1667. So for multi-gigabit data transfer, this turns out to be a few megahertz. So you integrate the phase noise from a few megahertz up to Nyquist clock over 2. Wireless standards, on the other hand, care about both low frequency and high frequency noise. They specify spot phase noise or phase noise mask, and they specify limits also for spurs. Spurs are concentrated amount of energy in phase noise. So when you look at one spur, imagine a sinusoidal modulation on the waveform. So in this case, for example, I have my carrier frequency, whatever it was around here, modulated by something close to a 1 megahertz sinusoidal. Okay. So these wireless standards specify phase noise mask, spot phase noise, limits on the spurs, and both narrowband and broadband integrated phase noise in some cases. For example, for data converters, RF DACs and RF ADCs, we care about broadband jitter, and for other LTE or GSM applications, this low frequency band matters and limits to the star. When we measure jitter in lab, for example, using an oscilloscope, we can decompose jitter into different components. So we talk about total jitter, whatever we measured on oscilloscope compared to the ideal location of the clock again. And I don't know if you can see some kind of vague histograms up here or in each picture. So this shows the distribution of edges on oscilloscope. So the TJ or total jitter is usually decomposed into 2 components. One is unbounded Gaussian component, which we call random jitter or RJ. So this Gaussian histogram, it basically indicates that unbounded jitter. If you wait long enough, you will get one event that's farther out here, and in theory, there is no bound to this jitter. We define the RMS value of the jitter, and to get the peak-to-peak, we need the depth of measurements. So if you're interested in a bit error rate of 1e-4 or 1e-6 or 1e-12, you have to wait long enough to get that many bits without error, right? And if you wait that long, the tail of your Gaussian distribution would hit a larger number. So we define a Q factor, which is a function of target bit error rate. And this is listed here in this table at different Q bars or Q factors for different bit error rate targets. And obviously the lower bit error rates, meaning smaller numbers down here in the table, means the depth of measurement is more, and you will get a larger multiplication factor. There's also a subtle difference between a clock and data. So there's a transition density. For data, it's 0.5, and for clock, obviously, every time you get one edge on each clock period. So transition density is 1. So the numbers in these 2 tables are slightly different based on that transition density. And all of these are coming from the Gaussian distribution or a inverse Gaussian distribution. So your random jitter, if you have the RMS number, you multiply it by 2 Q factors and you get the peak-to-peak. Then you add RJ peak-to-peak to DJ peak-to-peak to get your total jitter peak-to-peak. All right, so this is up to this point. DJ was the deterministic jitter. It's bounded, right? So it's not random, it's not unbounded, and it has different components in it. So one component, we call it bounded uncorrelated jitter. So if you look at this histogram here, you see distribution, but it doesn't look like Gaussian. It looks like there is a limit to it, right? For example, if you have power supply noise, it's usually coming from the activity on chip, which is somewhat deterministic. It may have a random component on it, and that goes to the RJ category. But the rest goes to bounded uncorrelated jitter category, as long as it's not data dependent and as long as it's not periodic. So those are the other components that you can get on a jitter. So you may have data dependent jitter or DDJ. And this may be a duty cycle distortion, or for the case of data only, this may be just intersymbol interference or ISI, right? So duty cycle obviously can be on clock or data, but ISI is only for data. And then comes the last component, which is periodic jitter. We talked about it before, so it's kind of like these spurs that are modulating your clock at certain frequency or offset to the clock frequency. So period jitter is very deterministic because you know the modulation frequency and then you know you measure the peak-to-peak value. So in phase noise domain, we show spurs as a DBC. So we basically put that integrator filter around this region and calculate the total energy concentrated around 1 megahertz in this case. Measurement equipment does that automatically. Then instead of DBC per hertz, since it took the integral over this local neighborhood, it will report DBC. So those spurs are listed in a different unit and they are overlaid on the spectrum of phase noise, which is DBC per hertz. So don't mix up period jitter with periodic jitter, okay? So you got that. Any question up to this point?
Hi, Harmaj. I have a question. This is Raz. You talked
Hi.
about cycle to cycle and periodic jitter and phase jitter, right?
Yes.
So, I mean, like given a phase noise spectrum, if we integrate, it will be a phase jitter, right? That's general phase noise, right? Like if you integrate and divide with the omega naught, right?
Yeah, so yeah, if you have the phase noise and you integrate it over like just look at this phase noise. If you integrate over different bands, you get different numbers. So you have to know your jitter filter, which is defined by the standard, and then you get an RMS jitter number out of that measurement.
Okay,
And
so now
takes me to this slide where I explain that different standards, telecom wants maybe 10 kilohertz to 20 megahertz, datacom wants F-baud over 1667 to F-baud over 2, and wireless may want both and more.
they're actual, right? May you know, like I understood, because I involved in datacom, so I know those limits. But a telecom does, I thought like the lower cutoff frequencies depends on like F-baud by like your CDR or whatever, but high frequency should be F-baud by 2, right? Independent of, irrespective of the standard.
These are some legacy standards that exist from the past, and for repeaters in optical systems, low frequency matters. You may get jitter amplification, jitter peaking in repeaters. And so most of these are related to optical systems, but the specs are defined that the source of the jitter may be electrical or optical. Measurements may be, again, at the optical interface. And when we design for these systems, actually the standard requires total jitter at the optical interface. Then we budget it into optical and electrical, because if my PLL generates a lot of low frequency jitter, it doesn't leave much room for that optical to electrical converter or electrical to optical converter on receive side or transmit side, right? So it boils down to budgets for the rest of the system, including the electrical. Yeah.
Okay, okay, got it. So last question is, I mean, so now you have a phase noise spectrum in the right side of your slide, right? So now like the period jitter. So you said period jitter is something which is like kind of, you know, high frequency parameter, right? So that means, does low frequency has no impact on that? Like say the period jitter is a low frequency, sorry, high frequency.
Yeah, so period jitter, you can, this is for timing mostly. So you compare the jitter or look at, you measure long sequence, you extract periods, you know, period 1, period 2, 3, 4, 5,
Yeah.
6, and you compare to ideal period. So now if you're, I guess maybe this cartoon, this animation helps. So if you have very low frequency, so this is like a, you remember I said the relation between period jitter and phase jitter is derivative. So derivative is, I guess in Laplace domain is S.
Oh, yeah.
So it's as if you find, you can find papers where they explain it mathematically. You get the phase noise and you multiply it by some kind of
Sync
high-pass function, sync function, but an approximation to that is just a straight line, which is the derivative. So for like most practical, you can just imagine it's a derivative, and yeah, that cosine function, I guess it's some kind of cosine function, right? Goes up like this, up to like this.
It's basically 1 minus Z inverse. I think
so that de-emphasizes low frequencies, right?
It's filtered, right? 1 minus Z inverse. Yeah, my question is, I'm trying to understand, like the period jitter is what do you call, it defines the timing, right? That's where actually you care about mostly. Do you know where can you find this cycle to cycle? In which application cycle to cycle matters?
Cycle to cycle is again for timing applications. I didn't find like a lot of relevance to SerDes, for example. It's mostly for timing, and again, it emphasizes the high frequency even more. So depending on the nature of your digital circuit, you may care about cycle to cycle jitter. Even though both cycles may be off from the ideal period, as long as they are close to each other, your timing may still work, right?
Okay.
Your setup time, hold time, depends on the nature of your digital circuit, but it emphasizes the high frequency even more.
Okay, thank you very much. Thank you.
Oh, my pen didn't work. I was trying to. Let me see. I get
one more question.
I get one pen on PowerPoint, one on.
One question, Hermos. 1 second.
Yes. Yeah. So this is trying to draw this. So if you multiply this kind of function.
Hermos, can you hear us?
Yes. Yes.
Okay. Sorry. Just a few questions we have.
Okay. Go ahead. I cannot hear you.
Am I audible?
Yes.
Yes.
Yeah.
You are.
Which jitter need to be concerned? Yeah, which jitter need to be concerned for clocking the high-speed ADCs?
Okay, so high-speed ADCs, we usually care about, again, like high frequency, and it's, I think I even mentioned here, even for wireless applications or wireline. So you care, but it becomes more like datacom, really, up to up to f-baud over 2, but it may extend even to lower frequency. I would say noise floor of your system matters a lot. So it's a broadband jitter, more like datacom.
Okay, sir. Thank you.
Hello.
Hello.
Yeah, Harmus.
Hi.
So when you are closing timing of an IP or an SoC, right? Like usually uncertainty will be like addition of PLL jitter and CTS jitter, right? Like how do we come up with that estimations? Like how much the PLL jitter should be or the CTS jitter should be for an IP or an SoC?
Yeah, so we, I guess in these 4 categories, when we get to digital clocking, so we report or specify maximum period jitter for these PLL. So that will be the uncertainty in the STA. So for example, if I say my PLL or digital PLL in this case has 40 picosecond maximum jitter, that's sort of what they can margin in their system, assuming there's no more, at least the source of the clock here will have no more than 40 picosecond period jitter, so that you can add as a margin into STA.
Any percentage like that? And how much do we need to over design? 10%, 20%? Any percentage is there?
Oh, okay. So that's a design issue. I guess it depends on. I guess I quoted a picosecond number, but a lot of PLL IPs talk about a percentage of the clock period. Yeah, so you can think about 5% or 1% or so. So this every PLL has a different performance, right? That's where the IPs differentiate from each other. But our latest digital PLL here for timing application has 25 picosecond maximum period jitter. So that's more like you can think about it as a peak worst case. So under no PVT condition, the period of this PLL will not be off from its ideal period by more than 25 picosecond, and that's a 3 gigahertz PLL. So.
Yeah, hi Harnos. So
Hi.
can you just give the impact of undeterministic jitter?
Sorry, let me go back to this slide.
Undeterministic jitter.
So we have deterministic jitter, which is DJ, and anything which is not deterministic, I guess we call it random jitter, RJ. So when you measure with oscilloscope, this is actually a typical report from an oscilloscope or advanced oscilloscope, I should say. It gives you total jitter, it gives you random jitter, deterministic jitter, and then further down, your deterministic jitter may have some periodic jitters. So it will tell you exactly what frequencies those periodic jitters are. You don't want them, but you may get a bunch of spurs like this on your spectrum, and these go to your periodic jitter component. It's very deterministic because you know the frequency of the jitter, right? And then if you're measuring data, data dependent ISI, but duty cycle is very deterministic. It's 2%, 1%, 5%, whatever you measure. And then the rest is kind of uncorrelated, but it's bounded. It's not like random. And this is very important category. It hurts us a lot, power supply noise and noise from the activity on adjacent lanes, the rest of the chip, right? Everything that looks uncorrelated to the activity of your PLL or SerDes. Because if you are generating self-induced noise, for example, your clock buffer just hitting power supply and generating ripple on power supply at the same frequency of the clock activity, that will not translate to jitter. The self-induced noise is usually okay, unless you get a complete brownout. If noise is uncorrelated to your frequency of interest from adjacent lanes activity of the rest of the chip, and it goes to power supply or through crosstalk or ground noise, whatever it couples to your circuit under test, it becomes a bounded uncorrelated jitter. But again, it's not Gaussian random. It has a bound.
I have a question here.
And
Shall I continue?
maybe
Thomas?
just to finish it, sometimes it's very difficult to, even for measurement equipment, oscilloscope, to decompose these components. So you may end up with a small periodic jitter, and oscilloscope is going to say, this is, background noise. This is, imagine if this spur was a little bit smaller, then it's going to say this is just, random noise, right? But, this is in principle, we have these categories. Go ahead, please.
Yeah, I have a question here. So how does jitter vary when you consider aging as a factor? Now it's all one to design the circuit, but over a period of aging, how does this jitter vary? Does a determinate jitter get converted into random jitter over a period of time?
Well,
as the device ages, right?
Yeah. So it won't get any better, right? And nothing gets better with aging, from my experience. But ideally, you ran or you factored in aging, and nothing should degrade much, or if it does, you factored it in through your aging simulations. Because now we have flow for aging simulation, but in the past we didn't. So it's just a little bit of extra margin. You cannot have a device that works now and then it passes a spec now and in 1 year fails the spec. So usually aging should be small, and otherwise, you may have to go and find out the underlying effects, such as NBTI, HCI, electrical overstress, something that degraded your circuit. You have to take care of that. It shouldn't happen.
Hi, Hermos. So I have a doubt. So in your slide of period jitter, you're talking about setup and hold times, right, for STA. I understand how setup time is, affected by the period jitter, but how does the hold time is affected by period jitter? Hold time is not generally dependent on clock period, right? So how does it affect?
Yeah, you're right. This was like a broad statement, but maybe cycle to cycle does. We provide these kind of uncertainties on the clock, and they are just factored in. Usually this STA analysis is pessimistic, so I wouldn't go too far into the last few picoseconds and worry about that. But yeah, you're right.
So I had a question on how, so on the phase jitter, does the functional mode of a VCO, that's the fractional or integer mode, does it contribute, how does it contribute to the jitter?
So your question is, how does the fractional PLL, the fractional mode of operation, contribute to phase jitter?
Yeah.
Right?
Right.
Yeah. so yeah, that goes more to, so fractional synthesizer usually works with some kind of, modulation on the divider, feedback divider, and the nature of it is deterministic. We usually, at least in our implementations, we use a delta sigma modulator that shapes the noise to high frequency and gets attenuated by PLL's low pass filtering. So in general, it appears as a bunch of, spurs. It's very deterministic because the modulation is deterministic, but it goes to high frequency and gets filtered. So we can still measure it. In fact, in this example, exactly, let me get my laser pointer again. So in this example, we see in the integration band, I have one spur, for example. I could have a bunch of spurs, and they could be from fractional operation of the PLL. Although in this case, if this is really a PLL, this spur is not supposed to be here, and it's not, fractional component we push to higher frequencies. But if we end up with in-band spur from fractional operation, a fraction which is near integer, that's sort of a bad fraction, and we cannot filter it easily. So it comes in band like this spur or this spur. And when you integrate over your jitter filter, it shows up as RMS jitter component. So yeah, bunch of spurs that eventually contribute to your RMS jitter, but they are, in nature, they are deterministic. Okay, so shall we continue?
Yeah, yes, please. No questions here.
Okay. So I have a, I guess, you continue on that fractional PLL question. I have a block diagram of a clock synthesizer unit, which we call CSU, or clock multiplier unit, CMU. It is a phase lock loop that multiplies up a reference clock input frequency. So you multiply up this frequency to a target output frequency. So your feedback divider is N, your output frequency of the PLL at the VCO output will be N times F ref. And then you may have another post divider which divides that frequency by M. So by changing N and M, you can change your output frequency. You may also have a pre-divider in the path of ref clock. So you factor that in the calculation as well. So here we have a phase frequency detector, block PFD, followed by a charge pump. And charge pump goes to a low pass loop filter. The loop filter here, this is a very popular architecture. So here we have a resistor in series with a large capacitor. This capacitor is an integrator. So this path is sort of like an integral path. We call this CZ in this example because it creates a zero in the open loop of the PLL, an open loop response of the PLL. So you have a voltage, integrated voltage here, and then for every time you get a correction, you get a blip of, charge pump current into this resistor. So this voltage across the resistor is we can call it a proportional voltage, something that corrects the phase quickly and keeps you in phase lock. Whereas this component, which is integrated on a large cap, is the integral component, and this voltage value practically sets your average frequency. So the control voltage here consists of an integral component and a proportional component. And the role of the second cap, which is a pole cap, is just to filter out this ripple a bit more to give a smoother voltage to the VCO. Otherwise, we will get more jitter. So this PLL may be integer n or fractional n. I'll explain the fractional implementation that we have done in many of our PLLs. The VCO itself may be a ring oscillator or LCVCO. LCVCO has better phase noise performance and therefore contributes to a lower jitter PLL, but obviously inductor takes more area to implement. Ring is more compact, also has more tuning range, because basically a low ring oscillator is more like a low Q feedback oscillator with equivalent Q of 1 or 2, whereas the LCVCO has a Q of typically at least 10, 20, and if we implement, if we have high Q resonators, I'll have more examples of that in our LOs. You achieve less tuning range and much better phase noise and jitter. So a little bit, I'm not going to give you in this presentation a lot of formulas, but I try to explain the concepts more. If you see a formula or two, they're going to be very simple. So this slide summarizes the phase noise analysis of a PLL. So PLL noise comes from different noise sources in the PLL or outside the PLL that are shaped by different transfer functions within the PLL. So here I list major noise sources of this PLL, which we saw in the previous slide. So we have the oscillator, VCO. The phase model of the VCO is an integrator. So it has a gain from control voltage, which we call KVCO. And then the fact that it's an integrator, it takes the integral of its control voltage and converts it to phase. So in Laplace domain, there's a 1 over S. So the phase model is KVCO over S. So if you imagine you have a thermal noise and a flicker noise, 1 over S gives you a slope of 20 dB per decade. So for an oscillator or for a VCO, your thermal noise has a slope of 20 dB per decade or 1 over F squared. And the flicker noise has an additional 1 over F on top of that. So it becomes 30 dB per decade or 1 over F cubed. The VCO noise within the PLL, within a closed loop PLL, goes through a high pass function and shows up at the output. So basically low frequencies get attenuated by the loop bandwidth because your PLL tracks the reference voltage, right? So it attenuates. If you have a free running VCO like this and you close the loop of the PLL, the low frequencies get attenuated, and anything above the bandwidth of the PLL, PLL is going to say, oh, I can't track that, or do anything about that. It's too fast, so it's going to just pass after the bandwidth frequency. It's going to pass the noise of the VCO to the output. I am not showing the peaking of these transfer functions here, so I'm a little bit simplifying them. So depending on the stability of the loop and damping, you will get a little bit of peaking on these functions. And this high pass, if you want to think about it a little bit more accurately, below the zero, which was formed by this RC, you will get the steeper slope on the VCO. But then you also have the flicker noise, which will go up. So I'll show through an example how this works. So remember, high pass function from VCO to the output. the next noise source component is the reference block. So it comes to the PLL. PLL is a low pass system. So it basically low pass filters the reference block to the output. And above the pole frequency that comes from this other pole, you will get even more attenuation. But F loop is the bandwidth of the loop, which is close to the unity gain bandwidth of the open loop. So this is the bandwidth of the closed loop. Again, I'm not showing the peaking in the transfer functions. This function is known as jitter transfer function from the reference. Some standards that specify the jitter transfer function from reference to the output. It has to have certain bandwidth. For example, PCI Express, they tell you that your transmit PLL and receive PLL need to be within this bandwidth range. For example, 2 to 4 megahertz, or for the latest gens, Gen 6, 500 kilohertz to 1 megahertz, etc. And then peaking has to be less than 2 dB. And some other specs say less than 1 dB. The other noise source is the PFD charge pump and feedback divider. So if you look at these guys, they go basically through the same low pass transfer function. So the transfer function will be similar to the one applied to the ref block, right? So same low pass function, but the noise itself may have a different shape. For the input ref block, because it's an oscillator, it has a thermal component, 20 dB per decade, a flicker component, 30 dB per decade, and it's probably a buffer on board or something like that. So eventually you hit a noise floor for everything, right? So especially on the input ref block, I'm showing a noise floor here. For PFD charge pump and feedback divider, they are not usually big contributors to phase noise, but if your PLL has high bandwidth, then they contribute more, obviously. So you have the thermal components is like a floor, and then if you have a flicker component, it will be 10 dB per decade. The loop filter, again, it's not usually a big noise source, but you have at least a resistor, maybe 2 resistors right there. And you may have another RC, for example, here, right? And resistors thermal noise. So the density of this thermal noise is power spectral density of voltage noise, basically due to the resistor, is 4 kTBR. And this gets shaped by a band pass function and through the PLL. So if you write the transfer functions, it turns out that you have a band pass, which is from the 0 to the loop, to the bandwidth of the loop. Power supply noise, I assume that power supply noise is not shown separately here. It may affect each block, and it's pretty important actually to factor that in. But the behavior on each block is going to be different. So eventually, if your VCO has power supply noise, it gets noisy and it goes through this transfer function, right? Whereas if your input ref block and buffers are picking up noise, it will go through low pass transfer function and so on. And then if it couples to the loop filter, most of the time, you see this kind of transfer function from power supply. So the next slide, I'm putting this a little bit more into practice, starting from an oscillator, noise shaping in the oscillator, which I explained almost already in previous slide, and then I'll show you the whole PLL. So usually oscillators are followed by some kind of amplifier or buffer. to prevent the loading and give you the swing that you want. For example, for the ref block, or the VCO itself may have an output buffer, right? So in general, this output buffer has a white noise floor. So it's the amplitude noise that modulates the delay of the buffer and converts to phase noise. So this is more like a floor. We call it, white phase, right? And if this is not a simple buffer, if it's an amplifier and VCO is low phase noise, you may actually see the flicker noise of the amplifier also contributing. So if you see a 10 dB per decade in your measurement or simulation, it's probably most likely coming from this amplifier at the output of your oscillator. Then the oscillator itself, as I mentioned, it's an integrator, so you should see a 20 dB per decade for the thermal component of that. So it's called white frequency. So basically phase is converted here in the oscillator to frequency. And this is the thermal or white region, so white frequency and then flicker frequency. So these are different terminologies you may find. And then there's sometimes if your oscillator is actually drifting in frequency, so you may see a -40 dB per decade, which is in literature called random walk-off frequency. So I'm not showing that here. I'm assuming enough stability. But if when you get close to the carrier, you see all sorts of garbage like that. But fortunately, the low frequencies, when you close the loop, they get a lot of attenuation and log to the reference, which is usually a quartz crystal and very stable. So when we put all of this together in a PLL, we get this. And so again, I put this block diagram as a reference here, and I try to color code it a bit. So the oscillator and buffer in yellow. So you may have a noise shape like this coming from the reference, which then gets attenuated by the bandwidth of the loop. So above the loop, so this is the closed loop basically. Above the loop, the ref clock gets attenuated. So it had a floor and everything, but above the loop bandwidth, it goes down basically. You won't see the much effect of the buffer noise floor at the output of the PLL. Then the blocks color-coded in red, feedback divider, PFD charge pump, they go through a similar low-pass function, but on their own, they may have higher or lower noise. This is an example, yes, right? So this charge pump PFD has some noise floor and then a flicker, thermal noise and flicker noise. And then above the PLL loop bandwidth, it gets attenuated. Right? Remember I said if you have a wide bandwidth PLL, you worry about the charge pump noise and PFD noise because you allow more of this noise to go to the output. Then the blocks that I color-coded with green, I guess the darker green or the thicker line here is the VCO. Right, so remember this VCO had it was something like this, thermal and flicker, and it goes through this high-pass transfer function. Right, so the end result may look like this. So VCO dominates basically above the loop bandwidth. The VCO noise dominates. And then around the loop bandwidth, it gets attenuated. Below the zero frequency, it gets more attenuated. And then the flicker noise kicks in, and you may see a little bit of even higher noise from the VCO here. But usually in band, you have other components. In this case, the ref clock at low frequency contributes more. So the dashed line is a combination of everything. The loop filter, remember I said it's usually a small contributor and it gets shaped by a band pass function. So just imagine a white noise from a bunch of resistors and it gets shaped by a band pass filter. If you choose very large resistors in your loop filter, or if you have a very clean VCO, such as resonator, bar resonator, PLL, and I have a few examples of that later, then you worry about all these components. But in this example, VCO, the main sources that dominate are VCO above the loop bandwidth and charge pump mid band, below bandwidth, and then the ref block at lower frequencies. And then anything outside the PLL loop, in this case, I put this buffer and post divider outside the loop. So this is amplitude noise, basically. It's more like the floor of the system, right? The blue line. And it doesn't get attenuated by anything, right? So this sets the noise floor of your system. So the noise floor is coming from this output buffer, post divider, as well as the VCO itself, but at higher frequencies, VCO goes even lower and lower. So the dashed line is power sum of everything. So this is the output of the PLL post buffer and divider. And then this was a small signal model that I forgot to mention, but I did mention already that VCO was an integrator. Loop filter has a transfer function from charge pump to control voltage. We just write down H of S. PFD charge pump model is simplified to ICP over 2 pi. So every 2 pi, every cycle of ref clock, it gives you one correction pulse. And stronger charge pump just gives you more gain in the loop. And these noise sources are just modeled by this phi of VCO or phi I noise of charge pump or phi of feedback divider. They're adding them to the ideal model, small signal model of the PLL. Feedback divider is more like an attenuator. If you have a divide by n, you have 1 over n in the feedback path. Okay.
Harmos, if it is okay, can I request for a break?
Yes, I think we are right at the beginning of the next chapter section, so we can go for a break.
Okay, thanks. So
is there any quick question?
we have a
right
question,
now?
looks like. After that, we'll take a break.
Okay, okay.
Yeah. So Hormuz, the phase noise which you talk about, the PLL as a whole, when we simulate, which analysis, should we run to plot the phase noise? Should we run PSS plus P noise or HB noise or transient noise for a realistic simulation time?
Yeah, you can, there are different methods you can do all of the above. So some people like what we do, we run on the oscillator, for example, as a main contributor, we run PSS P noise, or for speed, you can run HB noise, right? So you get the profile of the VCO. Then we actually build a small signal model of the PLL like this. In MATLAB, you can also build a similar model in a Spectre. And the Spectre model will be more accurate actually, but the MATLAB one runs faster, obviously. So in the Spectre, you capture all the parasitics of the loop filter and real impedance of the charge pump or output loading that comes from charge pump or variation over PVT of the charge pump current. So it's still a small signal model, but a little bit more realistic if you build it in a Spectre. And in that model, you feed it with a noise profile that you found already from the standalone VCO simulation. So you piece together these components. And it's much more understandable, and you can debug it and improve it. If you see noise is coming from your VCO, you feed it with a real reference clock noise. All of this is in the phase domain. As you mentioned, you can run transient noise. It's a little, more time consuming. It's the whole PLL, and it gives you less insight, but I'm not saying it's not doable. A lot of people do it this way, sort of like a brute force. Like in the end, at the end of the design, I wouldn't disagree if you want to run a transient noise simulation. But to start your design and to optimize your design, it doesn't make sense to do it with transient noise. Just maybe as a final verification on top of all the other PSSP noise and small signal loop simulations that you did, and do a transient noise in the end.
Sure. Thanks, Hermos. So we'll take a bio
You're
break
welcome.
for 15 minutes and we'll resume at 3:20 p.m.
Okay. Thank
Thanks.
you, everyone.
Yeah, you can stay online, Hermos. We'll be back.
Sure.
Harmos, I am also online. Can I ask you something? So when everybody is in the coffee break.
Sure, sure. Please go ahead.
Yeah. So Harmos, in the phase noise, right? You mentioned, like whatever slide you are showing now, right? In the right side. So like again, my question is only cycle to cycle and all. So given this plot, can you say, because that is something, because I've been building PLLs, but that's something which I haven't, get the confidence, like, given that, let's say, given the design, if you are targeting, if you want to improve the period jitter, which component you attack? I only know the integrated always, like I try to, like get the, play with the bandwidth and play with the noise of individual sources to minimize the area. That is the only one game I play. So if you want to minimize the period jitter, so can you identify, okay, VSO is the reason or reference is the reason? Can you identify like that?
Yeah, each design is different. Period jitter has, again, its own components. So if I take you back to, so this jitter decomposition, although it was the story of phase jitter, but even period jitter has a random component and a deterministic component. So in our digital PLLs that we use for timing purposes, if it's more like high performance version of it, the period jitter contributes. If it's a digital PLL, you have this quantization noise that's coming from
EDC.
the digital. Yeah, so you switch your VCO even or between two different periods, and that creates a period jitter, right? So that's the deterministic component. So if your oscillator is a DCO, a digitally controlled oscillator, you modulate it and your PLL is locked, and so you never stay on a fixed period, right? You're constantly modulating back and forth between two adjacent quantized values of the period. So that step is one deterministic component of period jitter. The random component is always there. So we actually run phase noise on that. And the one that I explained how you apply the high pass function on the phase noise, right?
Yeah.
So you can analyze it like that, or in Spectre, when you run simulation, now there is built-in function that gives you the period jitter random component. Before we get these, like a few years back, we actually manually applied this kind of high pass function. We get the normal phase noise, phase jitter, and we apply that mathematical function. But you can now just run simulation for the random period jitter component, and then convert it to peak to peak for your target application. Then there's always like the one important component is power supply noise. Right? Remember I mentioned that all these transfer functions are, assuming no explicit power supply noise. There may be this profile, part of it may be power supply noise, but if you have sensitivity to power supply, then you put certain amplitude peak to peak on power supply. So if you're limited and you specify it to the users that noise on this supply cannot be more than 50 millivolt peak to peak or 20 millivolt peak to peak or whatever, right? So
Yeah.
you need to make sure certain quality of the power supply, and then in your simulation, you simulate to see how that kind of noise converts to jitter, and that's
Yeah.
an additional component on your period jitter. Yeah.
Okay.
So there's a little bit of budgeting and decomposing jitter, I guess, into different
Yeah,
components.
yeah. My point is, I was thinking that like after, I think, yeah, I got a very good understanding after your first introduction. Like since you talked about period jitter is like high frequency only, right? Mostly because low frequency. So like mostly the high frequency is VSO limited, right? So so it's mostly, I think, if you tweak a bit of VSO, does that improve? Like that should improve period jitter, right?
Yeah.
Okay.
And if you want to attenuate more of the low frequency, I guess you push out the bandwidth of your PLL, but then be careful if your reference block is not clean, then you add more reference block noise. So
yes,
so sort of similar analysis, but
but that shouldn't affect period jitter, right? If your bandwidth is high.
Yeah, shouldn't have, like the high frequency matters most. If you have a lot of jitter on your ref clock and your VCO is also noisy, so you want to use high bandwidth, right? So you end up in a situation that you hurt your high frequency noise. That translates to more period jitter.
It's all trade-off. Yeah, understood. I think. Thank you. I think it was a nice explanation. And last one, I know if you want to take a break, you can take a break. I keep talking. So last question is, like for SerDes, I only work with SerDes groups, not wireless and all. I know in wireless, the reference pars matters, right? But in SerDes, where do you consider reference pars?
Like reference meaning reference clock, huh?
No, reference pars are the PLL, reference par.
Reference coming from the reference clock, right?
I mean, no, I'm talking about reference spars, the spar.
Yeah, that's fine, but as soon as you say reference, it just makes me think that it's the reference clock.
I mean, I'm thinking from any kind of spars, like even in the fraction spars.
Yeah. Okay, yeah. But then that's fractional spar.
Yeah.
So the reference spar, every time you get a correction, and every ref clock cycle, you get a correction here. So the ripple that I mentioned that exists on this control voltage, is a deterministic modulation, and that shows up as a reference spur. So you want that spur to be below certain limits. If you specify it in BBC, for example, if you have a very high bandwidth PLL, for example, you get a reference clock spur at the output.
Yeah.
Right. And anything above minus 40 dBc contributes to more than 1% of the period. So you worry about that at that point. But it's usually easy to just low pass filter the ref clock. So if you have a PLL, usually you don't use a bandwidth higher than 1/10 of the reference clock, do you? So if you end up in a situation that you want to use, you have a very aggressive high bandwidth, then you worry about reference spur. You also worry about the fractional spurs, because everything gets low pass filtered, right? Except for the VCO. Right?
Yes, got it. Thank you. Yeah. I'll let you take 5 minutes break then. So you'll be ready for the next session. Yeah.
Thank you.
Thank you very much, Aman. I got many things got, I think few confusions and misunderstanding of this, components like because I'm not that good in time domain based jitter, only frequency domain. So thank you very much.
Okay, no problem. You're welcome.
Uh, Harmos, I have one more question actually, if you don't mind.
Can you hear me?
I can hear you. Yeah.
Yeah,
I
because
can.
my headset is not on, but please go ahead.
Okay. So you have been explained to somebody how to simulate the phase noise, right? And I do the same, like, get all the blocks, P noise results, and then put it in MATLAB or Cadence. Okay. Like eventually filter through functions. Is there any way, like, we had several difficulties considering the, the noise folding of charge pump in fraction actually. That was like a very painful process and we never got to the bottom of that. Could you please explain anything on that?
So what was the problem? Like in a fractional
Yeah,
PLL?
in fraction, like how do you consider the, take care of the, like how do you account the folding of the noise, the nonlinear to the charge pump folding?
So in your model, presumably you have a noise model for the charge pump,
Yes.
right? And then when you modulate the PLL fractionally, yes, that there is noise folding. So this is part of your like top level that you unless you run that transient PLL sim, which sort of automatically takes care of everything.
Yeah, transient, yes, take care, but this kind of like, frequency
Yeah, you
domain
need
based.
to write, like in your model, you need to write a few equations to take care of that. For the integer and PLL, that doesn't matter.
Yeah.
Right, but for fractional, I guess there is noise folding in band. If there's anything, so small fractions usually become a problem. Right?
Yeah.
Armos?
Yes.
You want to take a quick short bio break or something? We're almost gathering back. Maybe you want to take 5 minutes?
Yeah, give me 5 minutes. Yeah.
Yeah, please do. Otherwise, I think you'll have a long session, right? Yeah.
Okay.
Yeah, I just texted a couple of things on the chat. You can probably look at it. I guess we need to speed through. We have 75 minutes after the restart.
So we'll resume back in 5 minutes. Please do settle down if you are done. In the interest of time, if everybody is ready, we'll start. We'll just wait for a minute. He's not back. Yeah, he's back. No, he didn't reply. Harmuz, you are there? Okay, I think he's there. Yeah.
Can you hear me?
Harmuz, you're back?
Yes. Can you hear me?
Yeah, we can hear you. Yeah. So almost everyone's gathered. Just allow 1 minute. We'll just do a quick quiz. We promised. Is everyone
Okay.
ready? So we'll do some 3 quick questions. Anyone who can answer, raise your hand. Don't say the answer. Then you will be giving up your gift to someone else, right? So just raise your hand and we'll see if you can answer, right? Ready? Okay. So we talked about many generations of building clock. So can somebody say how many generations of clocking circuits did the team do? Okay, you have to raise quick. Okay, I'm going to go with the, okay, you got the, yeah. What is the answer? 15? Okay. 15 plus, okay. Okay. Your good name? Okay, yeah. So he's, don't forget to talk to him, okay? He's going to give you the, okay, now it's serious, okay? No more fun questions. I think in the slides, Harmuz had low frequency noise impacts, which jitter? No, you have to raise up, get your mic, and you say your name and answer, please.
Can I answer? Raz from here.
Okay, it seems somebody has a mic. No, you're not eligible, okay? You have to be in the room because you cannot collect the gift otherwise, right? So we are fair. Who's, yeah,
hello.
Good.
It is period jitter.
Someone wants to try?
Phase.
I'm Neeraj. It's phase jitter.
You want a round of clap or? Okay, thank you. One more. In the equation for RMS jitter, he had 2x2 multiplier factor. So does anyone know what was the significance? Okay, there you go. Somebody's.
So myself, Anshul Verma, is the double sine phase noise. We have to measure double sine phase noise.
Okay.
Okay, measure is the single sideband and the upper sideband. So we have to measure both sideband noise. That is the we have to multiply.
You want to say double side?
Correct.
Okay.
To measure the jitter.
Great. Yeah. Good. So I think he was definitely paying attention, right? You had more tea, coffee? Not the lunch we had? Okay, good. Okay, we'll get serious now. Harmos, back to you.
Okay.
So we'll have a few more at the end for sure. And you're definitely going home laughing, okay? Or smiling, actually.
Harmos, can I request you to little speed up in the interest of time?
Yeah, we just finished.
More
the
or close to.
Yeah, we just
I
finished
think,
the introduction.
You still have 40 plus slides, right? I guess we'll have to rush through or
And
skip a few.
I thought I didn't have enough slides. Okay.
We don't want to trouble you too much too. Okay, audience also, questions also, please.
Okay, so I guess the second section after a long intro is we focus on our series PLLs, and it's basically our clock synthesizer units that clock is transmitter and receiver in the SerDes applications, wireline applications. So we define figure of merits for all of our IPs. So for PLLs, for this kind of PLL, we define what we call form P, which is product of power, PLL power consumption in watts and RMS jitter in seconds. So watt times second becomes joules. So the unit of form P is joules. So you can think about it as a process that draws power from power supply and generates a clock, but the clock is not ideal. So you want that power draw to be as small as possible and the jitter of the clock also to be as small as possible. So we track this form over time now for nearly 20 years. And I listed some of the data, like I picked a few representative PLLs from each node, each technology node, and I listed it here. So starting from 0.18 micron, which was actually a ring oscillator for SONET applications, 2.5 gigahertz application. Then we moved to LC oscillators. This is in 0.13 micron. Then we moved to 90 nanometer, 65 nanometer. The rate increases 8.5 gig, and then we have 11 gig. In between, we have other rates, 6 gig for SAS2 or 10 gig for EPON, etc. But if you look, this is versus time. Even in a given technology node, we may have 2 generations, and we try for every new round of design, we try to improve this form, figure of merit. So we track it to stay in the best in class. So we try either to reduce the jitter or power or both. Along with that, some of these PLLs started adding new features. So earlier PLLs were integer n, then we add fractional n, and then what we call gapless in frequency, meaning that the whole PLL combined with post divider will generate any frequency below its maximum limit. So if it's one example, I guess, of a gapless was this 8.5 gig PLL. So any frequency below 8.5 gigahertz in any band for any standard, we can generate it. And of course, part of this is to be fractional, but being fractional is not enough. You need to have coverage over all bands of frequencies. So we add these features in every generation. So overall, this kind of improvement, you see that we go almost over 60x improvement in form over 20 years. So this is coming from a combination of process node scaling. That's part of it, but it's not enough. Within a process, we also see improvements. So there's architecture evolution and circuit techniques that we apply. Some of the examples, I list here, obviously going from ring oscillator to LC-VCO gives me lower phase noise and jitter. We at some point we went from CML architecture, from these old day ring oscillators, or even the first generation of LC-VCO, there was a lot of CML circuit there and it's burning more power. So we switched gradually to CMOS and to single-ended, and it didn't hurt the jitter much. It actually saved us a lot of power. And remember, we have to integrate hundreds of these PLLs on each die. So that, you know, the power improvement definitely for these service applications is very important. We went from high voltage, some of the older PLLs used high voltage and low voltage supplies to low voltage supply only. So again, less complexity and lower power, a lot of circuit optimization at transistor level, optimizing the Q of the inductors, adding tail filter to these VCOs or common mode resonance technique that in some recent LCVCO papers, those techniques are described. You know, all of these to improve on phase noise and jitter, simulation, modeling, enhancements. Like I said, early days, we didn't have all these great jitter and phase noise simulation tools, but now we are getting more and more accurate, even those tools. You know, even when they started, they were not very accurate. We do a lot of power supply filtering in the package to isolate underlying circuits from each other to avoid that kind of bounded uncorrelated jitter that I mentioned. That's one component of improvement, but this complexity is having so many PLLs and SerDes on one product. And then adding LDOs on die is a new dimension to that. This is always coming with overhead in power and area, but at some point, power supply filtering in package is not enough. So we lived with this for many generations, and now we are adding, on top of that, we are adding LDOs on die. In literature, if you look at papers, in academic papers, you see other definitions for a PLL form. So this is one definition, which is in dB. That doesn't matter, 10 log of something, right? But the important factor is PLL power and RMS jitter. But this academic definition has RMS jitter squared. So it is correct. It's just a different form. We didn't use this definition first. We just went straight with power and RMS jitter. And the reason for that is you can always, when you go from this generation of a standard to the next one, let's say the rate doubles and my standard requires half the jitter, right? So I can always in this formula, if I want half the RMS jitter, if it's most of it is random jitter, for example, I can quadruple power and it doesn't hurt my form, right? And if I do a little bit less than 4 times power, then I improve the form, hooray. No, we didn't want to do that. This definition is more aggressive, right? So it's more aggressive, and we didn't want to allow ourselves to increase the power so much just to get a lower jitter, right? So we went with this definition, and it looks like, you know, at some point this is plateauing, and it does. At some point, the form degraded in this generation. I will explain it next. This is where we started caring about area. We went with hybrid analog digital PLLs. And in the first generation, area improved, but power went up a little bit because of the extra digital circuit we had. You know, if you do a fair assessment, you have to include the digital power. The loop filter went into digital, and there's a little bit of form degradation, but a lot of area saving. And then we are back to improving it a little bit. I replotted this same data with the second definition. So it's a little bit, you know, like I said, it's actually better. It looks like, oh, we improved it even more. But during the design, we don't want to use this definition because it's not aggressive enough. It shows that in the latest generation, 29 gig, this is our targets for 6 nanometer PLL, and design is nearly complete. we are improving the jitter, right? And here it has more weight. So although here it looks like we are plateauing, in real life, we are doing the right thing and improving the jitter for this without improving the power much. So I think I said enough on this slide. So I just want to explain these two dots, why in this generation form degraded. This is another form chart, but this has to do with area. So technology scaling usually gives us area scaling, that's nice and simple. But when we moved from 28 nanometer to 16 nanometer, there was a lot of density rules and layout that hurt the MOS cap density. And also there is some components in our PLLs and any high performance PLL like inductors and flip chip bumps, and they don't scale much with technology node. Right, so the analog PLL in 40 nanometer to 28 nanometer, we still wanted to get improvement, but these density rules, even in 28 nanometer, sorry, I have to emphasize that, even in 28 nanometer, these density rules were hurting us, and the analog PLL estimate was not much less area than the 40 nanometer version, maybe 10% lower area. So we went to this hybrid architecture for the first time here. In the hybrid architecture that I'll show in the next slide, we implement the loop filter, the large capacitor of the loop filter in digital. So it's a digital implementation. That saves a lot of area. And one advantage of this is for low bandwidth PLLs, such as jitter attenuators, for lower and lower bandwidth, you need larger and larger capacitors. So even some very low bandwidth PLLs have external capacitors in some RF application as a jitter attenuator. So all of that, when you implement it in digital, it's just a larger accumulator in digital, for example. Right? So this hybrid implementation with digital loop filter is very nice and gives us a lot of flexibility and portability. Right, the trade-off, as I mentioned, was a slightly higher power due to the digital portion of the PLL, that's something that we can continue to work on and improve. So this is the block diagram of a hybrid PLL, something similar to what we have implemented starting from 28 nanometer and into 16 and 6 nanometer as well. So here, if you remember my earlier slide on PLL, I had, I can do a quick flashback on this. I had the integral component on the capacitor, which we now implement in digital, and then I had a proportional component of the control voltage. Right, so here we explicitly split these two paths, and we have still a charge pump and a proportional loop filter, but it doesn't have a C0 large capacitor. Instead, we have an integral path in which some kind of bang-bang phase detector or binary phase quantizer out of the linear PFD that sends us this, implements this integral path, right? That voltage that was built on that capacitor, right? So the digital integral path includes an accumulator in digital and a DSM with some sort of thermometer coding coming to a DAC. So eventually you have a voltage here, an integral voltage, slowly moving and correcting the loop to keep the frequency at the target frequency. And the output of that, we also have a small loop filter to make this voltage smoother. So they go to different reactor banks in the VCO so that they add up. So effectively that resistor and capacitor, right, is implemented, equivalent function is implemented here with much less area. So this portion, everything in orange or yellow is implemented in digital and blocks in green are in an analog, right? So this is the example of a 12.5 gigahertz PLL. Then we have a post divider bank, and it gives us the half baud rate output clock for the SerDes. So the 16 nanometer performance here, you remember from previous slide, I mentioned 30% area saving compared to an analog equivalent, right? And without this, we wouldn't get much area saving just by a scaling technology. The RMS jitter of one of the PLLs in this generation, we have 2 or 3. The best one is in the order of 220 femtosecond typical. The next slide, I'm gonna talk a little bit about this fractional feedback divider implementation.
Harmas, one question. How do you compare to ADPLL? Oh, I mean, how does this HPLL improves? I mean, same loop filter area improvement will happen in ADPLL as well, right?
Yes, yes, but this is more high performance because there is no quantization on the proportional path.
Yes.
So you almost have a charge pump PLL with continuous analog loop filter correction.
Okay.
Without the overhead of the area. I guess first time you design it, it's more complex, but it's the digital portion of it is very portable. So then in the next node, you just port the digital and put the rest of the analog together. So hybrid PLL is still more high performance. You get the performance and you get the benefit of area reduction. There are all digital implementations in literature. They're becoming more and more popular, but this is more like to keep the analog performance intact, because we are at the same time, we are not supporting the same standards. We are moving to higher rate standards. So we continue to need even lower jitter, right? And we are taking it step by step, which is a hybrid effort.
So just to summarize, right? Basically, like your what you call quantization noise and all better in terms of you are better in terms of quantization noise. So maybe phase noise is better, something like that.
Yeah. So I'm not like in all digital PLL. There is going to be quantization noise from in the loop filter, whole loop filter. I guess it's even proportional path, right? So
yeah.
Was it with you? We were discussing the DCO switching back and forth between two quantized period values, right? But this LCBCO, there is no switching happening on it in the proportional path. So, and an integral path is very slow and low pass filter.
Okay, thank you very much.
You're welcome. So this is the sort of high level drawing with a little bit more details of how the fractional feedback divider is implemented. In terms of performance, we have this in 16 nanometer. It works up to 18 gigahertz in worst case, slow corner. It consists of 4-stage cascade of div 2 or 3 cells. So each cell can do divide by 2 or 3, and then we have 4 in cascade. So with this, we can cover divide ratio from 2 to the power of 4, which is 16, to 2 to the power of 5 minus 1 to 31. So this is basically a fast divider, a multi-modulus divider, MMD, that divides from 6 to 31, and its maximum speed of operation is 18 gigahertz. So we use this in our 16 gigahertz VCO, so we have a bit of margin between the maximum VCO frequency and the worst case performance of the divider. So this divider is controlled by digital. So the whole divider system works like this, that this divide ratio controlled by digital code divides the VCO clock down and we send a feedback clock to digital, then here we have another, what we call a slow divider, which is really a counter. So we count the cycles of this MMD, anything between 2 to 127, depending on what total divide ratio we want to implement. For example, if you wanted to divide by 32, that's simple. You just count 2 cycles of 16, right? And if you wanted something higher than that, divide by 50, for example, you can count 16 twice, and then third time, I guess you add 18. You can do anything between 16 and 31, right? So basically, we by this controller controls the high-speed divider and it counts with different divide ratios, and overall it implements the final divide ratio that we want, which is in anything between 32 to 2047, right? With 127 times, 126 times 16 plus 1 time 31, I think adds up to 2047. And then the fractional modulation is basically a third order delta sigma modulator with their option. So the input to this is a numerator and a denominator, 2 fixed values, which define a fraction. And then it makes this modulator jump between 2 integer values effectively to implement a fractional value. Right, so basically in digital, we have low speed counter and a delta sigma modulation for fractional operation. And then the accuracy of this is a 40-bit DSM, third order DSM, so it gives us accuracy in, this is, I guess, 1000 ppb part per billion. So basically it's in any fraction we want, we can implement with this in terms of resolution. In the next slide, I want to not totally change the subject, but talk about an interesting technique that we use for first time. I guess we are implementing many LCPLLs on die. Remember, I mentioned that we have to implement this in a dense manner. So these LCPLLs are put next to each other because we have, nowadays we have more than 100 such PLLs. This was the first implementation, and I think it goes back to 65 nanometer where we had 20 SerDes PLLs next to each other. And before that, we had a test chip with fewer of these PLLs next to each other. And when PLLs and VCOs are running at a small offset, this condition is known as plesiochronous. They are basically running at the same nominal frequency, but a small ppm offset because they may use different ref clock sources. One of these PLLs may be using the timing from a recovered clock, which is the far end. It's coming from across the ocean or something, there's a data stream coming and we get the recovered clock from that. So there's a small offset between these reference clocks going to these PLLs. And 2 PLL with a small offset, we observed magnetic coupling between the inductors. So this plot here shows an experiment we did in which we swapped the offset frequency of one PLL versus the other. And if they are running perfectly synchronously, meaning at 0 offset, we got to the minimum jitter of the PLL. In this case, we are reporting the TJ RMS. So total jitter, remember, consists of both random and deterministic components. So this is a TJ of 0.4. So it's basically the performance of one PLL without any coupling. But then when other PLLs coupled to that, we noticed that without doing anything else, this TJ increases from 0.4 picosecond up to 1.4 picosecond for 2 lanes. And if you have 3 lanes, it goes up to, or more, goes up to 2 picoseconds. So there's a lot of performance degradation or higher jitter if we don't do anything about this. Solutions to this, we still remember wanted there's dense per lane integration of LCCSUs. And there wasn't a lot of literature at the time for this. So there are many techniques used nowadays, ranging from inductor shielding to using inductors that are inherently low in electromagnetic interference. And what we did here is different. We use the shielding and obviously brute force spacing. So you want to space these PLLs a little bit more, but not too much, right? Because it wastes area. So we used an alternate frequency plan for odd and even lanes that I'm showing in this picture. And it's explained a little bit better in this paper we published a few years later. So for example, this simple example I'm giving you here, I want to support TX clock for a 2.5 gigabit per second lane. So the half rate clock of this is 1.25 gigahertz, right? So if my VCO has enough tuning range and I have two post dividers, divide by 3 and divide by 4, I can generate this clock using a 5 gig divide by 4, which was the main design or main targets of how to support this rate. But we have frequency redundancy. So we have large tuning range and we have more post dividers. So this alternate lanes, every other lane has a 3.7, it tunes its VCO to 3.75 gigahertz and divide by 3. So it gives us still 1.25 gigahertz. Now these VCOs are so far apart that they don't couple to each other anymore. Again, the coupling is only when you are at a small offset, and it's around the bandwidth of PLL. So if you look at the x-axis here, 500 kilohertz or so, there's even a little bit of peaking. So this is related to that those transfer functions on Mary mentioned, because one VCO is victim and the aggressor is the adjacent VCO. So it couples the noise, the delta frequency between the two VCOs, and it acts like a mixer. It generates a spur in band of the PLL, and if it's in band, it doesn't get filtered. When you increase the offset frequency more and more, that spur goes out of band gradually and gets attenuated. And if you go to lower and lower frequencies, you remember the transfer function from the VCO was a high pass. So this, you get more attenuation also. So the worst spot for this coupling is around the bandwidth, where you also have a little bit of peaking also in transfer function. Now, continuing on that topic, I'll talk about a few VCOs with special inductors. So the first one shown here is in literature. It's known as figure of 8. So you have two loops with partial magnetic cancellation at far field. So if you look at the direction of the current in the loops and you use the right-hand rule outside the inductors, along this axis, the H1 coming from loop 1 and H2 magnetic field from loop 2 cancel each other along this axis. And everywhere else you get at least partial cancellation, right? So in this is a very simple version of this inductor. We have a more elaborate version of this implemented in our 16 nanometer VCO. This helps attenuate the VCO to VCO magnetic coupling, but there is a trade-off with the quality of the Q factor of the inductor. So this inductor has a little bit lower Q, and our version is a little bit more elaborate, and you can work on the inductor design to improve the Q, but inherently there is a trade-off here that I'm mentioning. Then we have a patent on a more generalized version of what we call a reconfigurable multi-core LCVCO. This is somewhat related to our high performance local oscillator implementations for RF applications. I'm explaining it here in this context because it seems relevant here on this slide. So in general, if we have a multi-core VCO, meaning you put 2, 3, 4, N VCO cores in parallel, right? You get lower phase noise. So they work in tandem, in parallel, and they burn obviously more power, but so the power adds up, but the RMS noise improves. So overall, you get with N core, you get 10 log of N improvement in dB in the phase noise. So if you have a 4-core VCO and like they run in parallel, ideally you get 6 dB improvement because you have like a stronger carrier, but the noise or phase noise is random and it doesn't add up 4 times. It adds as root 4, I guess. So this architecture is a reconfigurable array. So we have some kind of switch here. You have to make sure that the adjacent inductors are having same amplitude and phase as the oscillators. Otherwise, you get a current that circulates between the two and that degrades the Q. So we have a calibration step, and then we can switch these, and there's very little current going across these and across the switch. But you can also flip the polarity. So you can get, when you go to the far distance from the array, you can get constructive addition or destructive addition of the magnetic fields. And so you can, I said there's a trade-off between Q and this EMI reduction. So with this, you can make it programmable. So you can not only program the number of cores that you want in parallel to trade off power and phase noise, you can also trade off the EMI reduction and phase noise.
Probably any questions still here? Anyone? Any questions? Okay, good.
Okay. So the next
Just
one.
a time check. We have close to 30 minutes, almost.
Okay. We're going to run out of time, but I'll go as much as I can. I want to cover the next chapter as well. There's 3 chapters left, but let's continue, push on. So this one is another special inductor that we patented, and it looks like you can think about it as we have 2 loops, and depending on how you drive, you program the polarity of these 2 loops. You can get coupling between these 2 inductors, and the effective inductance of the whole system, depending on the polarity between the 2 loops, will change. So if only one loop is running, let's say the baseline is L0 of the inductance. So it gives me maybe my LCVCO runs at the frequency of the dashed line. X-axis is the mom capacitors of the LCVCO. Y-axis is the frequency. Then if I have one polarity of the coupling, I get this self-inductance changes. K is the coefficient of the coupling between the inductors, and the mutual inductance is coming from K times the square root of L1, L2, I guess, right? So I can flip the polarity, and I can get L0 times 1 plus K and 1 minus K. So this mutual coupling between the inductors gives me a little bit higher inductance or a little bit lower inductance, depending on how I drive these mode selection cross-coupling switch, because this mode selection cross-coupling switch forces opposite polarities on the inductors here. If I turn this off, and I let this run by itself, I get same polarity between A and C. If I turn on the mode selection switch, I get the opposite polarity. So I have basically three modes. One was the base mode, which was only one inductor, and then the ones that come from 1 plus minus K. So this VCO works from, in one mode, from about 24.6 to about 28, or a little bit lower, and the other mode from that same frequency up to close to 36 gigs. So overall, you're getting 24.6 to 35.7 in a typical corner, which is a far wide tuning range, really, because you have 2 or 3 modes of operation. 2 modes is the one that we are using in practice, but there is a third mode if you run only one inductor by itself. So in summary, we have evolution of 30 CSUs across many technology nodes. I'm not gonna go through all these details, but I explained how we went from ring oscillator to LC and how we made the PLLs fractional and gapless to covering all frequencies above Fmax. Then we went to hybrid architecture to save area. Then we went to FinFET node and low EMI inductors, then wide tuning range VCOs, which I just explained, and we continue to improve the form in terms of jitter and power. Our current design is in 6 nanometer, nearly complete, and 3 nanometer is on the horizon next. So we'll start that later this year. And this is a summary of power and jitter from a few different technology nodes. So jitter is in the order of 340 femtosecond RMS in 65 nanometer, down to 250, 220 in the latest PLLs. And I have the form P and the area. Remember, the area went down for some time just with technology node. We are enjoying the technology scaling, and then eventually with this hybrid implementation. The next chapter that I'd like to cover is our RF PLLs. So in this section, we're going to talk about ultra low phase noise clocking required for our RFIC transceiver products that were used for wireless base station applications. The clock generator here in this world is known as local oscillator, LO. And the products, although they are a few years old, but the design and performance of IPs are still pretty interesting, and I'd like to explain a little bit of that here. The phase noise specs of these LOs for wireless base stations are very stringent, and they are driven by TX spectral mask specifications and RX blocker test to block the adjacent channels, basically. And these RFICs were supporting multiple standards and bands in LTE and GSM at the time. One of the toughest requirements was actually related to a low phase noise for GSM at a small offset at 800 kilohertz to 5 megahertz offset to the carrier. And it turns out that if we calculate the figure of merit here in terms of phase noise, the requirements here were 3 to 12 dB harder than a best conventional LCVCO that we could implement on die. So I'll show you how we address these in different generations. So we can say we had 4 generations. Here in this picture, first of all, I have to define this normalized form. So in this domain, power was secondary. So it's all about the performance. We only have couple of these PLLs on each chip. So power doesn't matter much. In fact, competitors have BJT solutions and external resonator, external VCOs actually So at the time we started, I'm not naming any competitor here, but I'm just comparing a few IPs we built and improved over time compared to what we were, competing against. And those, some of those have discrete components and they achieve very high performance form. Here, higher is better. So I take the absolute value of the phase noise and I add a term to any log of F naught to delta F, which basically normalizes this phase noise to carrier frequency and offset frequency. Because people report different things at different carrier frequencies, at different offset frequency. So this term normalizes that, and anything close to 200 dB in this greenish zone is good for most of the RF applications, except for the GSM receiver. All right, what we're doing here, basically, with between 200 and 205 dB, we had one type of solution with multi-core VCOs, and then above that, in the yellowish region for receivers, we mostly use resonators, in this case, bar resonator in package, which I explained. But more recently, even the greenish zone for more recent wireless applications, they require more demanding phase noise as new generations come in. So it's getting close actually to the performance that we required for RX GSM at the time. So, this is actually the cover of this Sedra Smith microelectronics circuit book. This is one of our RFICs on the cover of this book in 6th edition, I think. A lot of inductors, and then this region is the LO, right? Common for the rest of the chip. So the bulk acoustic wave resonator that I explained is a tiny component. So this is a thin film bulk acoustic wave resonator known as TF bar or just bar resonator. So it's a piezoelectric resonator. It's available in sub-gigahertz range up to 8 gigahertz at least. We did a system in package integration. And so we put these resonators in package here in this cartoon drawing, and there's package traces or bond wire. It's our implementations are all flip chip. Then you go to the die bump, and then this side is die basically. So you have your oscillator driver, whatever you implement, right? And it drives the bar, and this is actually one of our implementations. So the Q of these resonators in the order of 1K to 1,000 to 4,000. So it gives you a lot of low phase noise, because compared to a Q of 10 or 20 for an inductor. So this is not as high of a Q as the quartz crystal, but it's good enough to give you ultra low phase noise. On the other hand, this bar resonator doesn't have frequency accuracy as good as crystal or quartz crystal. So we have to kind of combine the two, or lock it to a reference, which we always do in a PLL. So we have a few different implementations that I'll explain next. This is the phase noise of a standalone bar oscillator at 2.5 gigahertz that we implemented in 65 nanometer technology first. So this is random jitter, integrated jitter from 10K to 29 megahertz is 29.8 femtosecond RMS. So this is a very low noise, down to 10 kilohertz. And in fact, we worked closely with the test equipment vendor at the time. This goes a few years back, to measure this level of jitter correctly, making sure that it's not test equipment, and that's mostly what's coming from our device. And if you put this into the, so this is the raw phase noise of this oscillator. However, this is still a free-running oscillator, okay? We're going to build a PLL around it. At 800K, this is the spec relevant to GSM, one of the toughest specs. And if you put this into that formula to normalize. Hello.
Sir, I have a question. Can you tell me what is the reference frequency for this?
This is still a free running oscillator. So we will lock it to a reference later in a PLL, and then the next few slides I'll explain that. But the reference clock is it's still in the order of 100 megahertz, a few hundred megahertz.
Okay, fine.
Yeah, I'll get to that. So the form from this BAW oscillator standalone is in the order of 223 dB. Remember, I said anything in this yellowish region was enough to meet our spec, but it's 12 dB, 13 dB tougher than a single LC oscillator. So, but we have a good chance now to hit that, because the standalone oscillator is 223 dB, right? So now we build a PLL around it. This is the block diagram of implementation of one of our flexible local oscillators for base station application. When I say flexible, it's because it has a few different implementations. One is single LCVCO for lower sort of, shouldn't say low performance, but something close to 200 dB form, okay? So, and 3 VCOs covering 3 different tuning ranges. So this is what we call single VCO. Then we have this quad core VCO. Remember when I said VCOs work in tandem, in parallel. So 4 VCOs give you in the order of 6 dB phase noise improvement. So we have 2 such arrays, so 2 quad VCOs. So this is another option we have. And then we have the BAW oscillator, so something similar to this, and the pins in package to put resonators in package. So nothing goes on board. So everything is basically inside the package from customer's point of view. It's just a little bit of extra cost to get these BAW resonators for the frequency you want, and then build the PLL around it. So the PLL still has a reference clock coming in, PFD, charge pump, all that. And this clock goes to a feedback divider system and comes back. So this shows the whole PLL still. And the dimensions of the die for this LO itself. This is the actual implementation of a PLL and the measured phase noise. So this one is a BAW oscillator in package with package traces. We create some inductance on purpose. And then we have capacitors on die. So this elements in red give me tuning range for BAW. Why do I need tuning range? It's because I want to lock it to a more stable reference. The BAW frequency is not very frequency stable, but if we get plus minus 4,000 ppm, and nowadays more expensive BAW, it comes even with the smaller, tighter frequency accuracy, then nonetheless you need to tune it with few hundred up to a few thousand ppm to compensate for trim inaccuracy and PVT variation and aging and everything. So these components gives us the tuning range. This is patented, and this is the performance of an LO with BAW mode, same BAW frequency, close to 2.5 gigahertz. So this is a single rate application. We see the phase noise of the overall PLL here. The RMS jitter is 100 femtosecond. If you, maybe I zoom in here a little bit. So it's 100 femtosecond RMS from 10 kilohertz to 20 megahertz. And you see the bandwidth of the PLL rolling off here is around 90 kilohertz. And there's a little bit of, hump here. This is where most of the fractional component of the noise is. It's attenuated, spread to high frequency and attenuated. So this is a pretty good performance. And at 1 megahertz, if you take the spot phase noise of 1 megahertz and put that into that formula, we get a form of 212 dB. You can still play with the PLL bandwidth. If I push the PLL bandwidth up from 90 kilohertz to 200 kilohertz, I get more attenuation even on the in-band VCO noise. And the RMS jitter was down to 72 femtosecond RMS, 10 kilohertz to 20 megahertz for the whole PLL. That the power of PLL here is 100 milliwatts. So this is the price that we pay to get this performance, because we have high voltage coming in and even charge pump, and everything is low noise. So everything matters here when you talk about 72 femtosecond or 100 femtosecond RMS. This is compared to our SerDes PLL, where the power consumption is in the order of 20 milliwatt, 15 to 20 milliwatt or so. The next slide, I show a multi-core VCO performance. So remember in this picture, I told you that we have BAW option and we have VCO array option, basically quad-core VCOs, and then we have single VCOs, right? So you saw the BAW first, and now you see the quad-core LC VCO, but this is a high voltage VCO, because one way to improve the phase noise of a VCO is to increase the swing. It's a signal to noise ratio thing. So we have a high swing VCO, and then we put 4 of them in parallel. We used ultra thick metal and a single loop inductor. So these are pretty high Q inductors on die, nothing comparable to the Q of a BAW, but sort of very good performance when you think about an integrated LC. So we have 4 cores in parallel working, and we are getting, ideally we get 10 log of 4, 6 dB improvement compared to a single VCO of the same quality. And in practice, we measured about 5.5 dB improvement, which is pretty good. This is higher power because now I have like 4 VCOs in parallel. So this PLL is in the order of 240 milliwatt power, but it doesn't have the cost of bar resonator and package. So basically allowing the customers of this radio chip to, based on their performance and the price that they want to pay, to choose different options. The PLL integrated phase noise is shown, closed loop phase noise is here. And the jitter is again with the bandwidth shown in this picture, which is 800 kilohertz. We hit 100 femtosecond RMS again. So this is higher bandwidth than BAW, right? Because BAW inherently had a lower phase noise. This is the performance of 4-core LC, high voltage LC PLL, which is pretty good. So the FOM equivalent of this is about 205 dB. The BAW version was what, 212 dB, right? And up to now, the story was about a single tone generation. So if you're working on this band, you can get the BAW and small tuning range, and that's it. Or you can get the LC, which gives you higher tuning range, but lower phase noise performance. Now I want to see how we can make this high performance and wide tunable. If I can cover this topic, I think the other chapters are probably not as interesting as this one. So what is the thought process here? We want to have a combination of LC-VCO and BAW. We want to make this thing widely tunable, basically. How can I do that? And still maintain low phase noise for low for base station application. So what comes to our mind is that, yeah, the quartz crystal have the best frequency stability, but they are limited to few hundred megahertz range. Therefore, for multi-gigahertz frequency generation, I need to have this multiplying PLL. So every time you multiply up a frequency by n, you get 20 log of n shift up in phase noise, which is degradation, right? But 20 log of n comes from multiplying PLL. So if I go through a divider, it's just the opposite. So it shifts the phase noise down by 20 log of m, but then my frequency is lower. So I want something for these radio chips in the range of 2 gigahertz, 1.8 gigahertz, something in that range, or another band is around 3 gigahertz. BAW resonators are available in multi-gigahertz range, but they are not frequency accurate. So I need to lock my BAW to this crystal LO, but then I don't get much tuning range. So how about the tunability? Can I use, so this is a thought process again. So can I use BAW for frequency generation around gigahertz range? And therefore I don't need to multiply it up or anything. So I get my performance derived from BAW, and I get my frequency accuracy from the crystal oscillator. Like I guess kind of covered that, but those components are in place, are part of the solution. And the tuning, can I use a mixer to make this thing widely tunable? So that's the next piece that we add to make it tunable. So there's a lot of theory and analysis that I cannot go into those details here, but the basic concept here is that mixer power sums its phase noise inputs. So if you have two inputs to the mixer, they power sum and go to the output. But the divider and multiplier are different. So they have this 20 log of n shift up or down, which comes from a divider. So if one input to my mixer is almost noise-free, I consider that BAW be very clean and almost noise-free, then I basically add 0 to this input, and phase noise of B goes directly to C. So basically mixer with one ideal input, the change of the output phase equals to the change of the input phase. So although it translates the frequency to a different frequency, the phase noise number will not change if one input is ideal. So I'm going to use that concept. So these are two concepts, like with multiplier and divider, and with the mixer. The math is different. So we came up with 4 different architectures, we got 4 patents basically. And this is the one that we implemented, 2 PLLs, and actually 3 PLLs, and one wraps around the whole loop. But I think I want to take you maybe to a simpler slide in appendix. So start from thinking about this as a PLL followed by an up-converting mixer. So you get a fractional PLL. This is here, charge pump, loop filter, VCO. Then I divide it by M. So this divider, remember, shifts down the phase noise, but the frequency is low, right? So it's not my target frequency. So now instead of multiplying it up, I up convert it, or I shift it through a mixer, right? With BAW oscillator as one input. So this phase noise number, which is good because it's after a divider, it just translates to a higher frequency and without much degradation. And then I close the loop. So basically I have a up-converting mixer in the loop of a PLL, and I close the loop for the whole thing why I do, why can't we put the mixer outside the loop? Because the ball frequency is not stable. So closing the loop on the whole thing compensates for any frequency drift of the ball. A small frequency drift, nonetheless, we have to log to the reference clock. So mixer and ball are in the loop of up-converting mixer. So I'm going to skip this slide, which is a little bit of example and calculations for that up-converting mixer. Equivalent solution exists if I have a down-converting mixer in the feedback path. Right, and why we did this is with the up-converting mixer, I still need to filter the side bands, and it requires a bandpass filter. It's actually more difficult to implement. Whereas with the down converting mixer, I just need a low pass filter, and then it's easier to implement. So this is the actual or still a simplified version of the implementation. The reference clock coming to this is coming from another fractional PLL, and then goes to this mixer PLL, wideband PLL. This is integer multiplication, except for the mixer part, which just translates the frequency. I want to give you through this example, just give you the concept here. So PLL2, the second loop, translates at 300 megahertz in this example. Input of 300 megahertz translates it to 9.6 gigahertz at the VCO output. So this is 32 times higher, right? Do you see my cursor still? So this is 32 times higher, but it's coming partly coming from up conversion, which is shift by 1.3 gigahertz. So this 9.6 goes through, divide by 6, and feedback gives me 1.6 gigahertz. And it mixes with a 1.3 gigahertz bar. So this is the bar or F bar, and down converts to 300 megahertz. I get two side bands, but with down converter, a simple low pass filter is enough. And I close the loop here. So phi n is phase noise shown in pink here, right? So I mentioned already that the phase noise going through a mixer remains constant, assuming the ideal input to the second input of the mixer. So this phi n at the PFT here, phase noise, same phase noise here, same phase noise here, going through the divider backwards. I guess divider goes from, this is a divide by 6. So input of it must be 6 times phase noise. And when you divide, it shifts down. So I'm just annotating these different nodes. And at the output, this is a divider outside the loop. It's programmable. In this example, just to make it simple, I'm putting it at the same divide ratio 6. So finally, it gives me a 1.6 gigahertz output. So I have effectively a 32 times PLL multiplier from 300 meg to 9.6 gig in terms of frequency multiplication. But in terms of phase, I only multiply by 6, because the rest of the frequency translation comes from the mixer, which didn't degrade the phase noise. Of course, mixer creates a bunch of spurs, so you have to frequency plan this carefully and also build a high performance mix IQ mixer with this low pass filter. Actually helped a lot compared to a band pass version, which was really difficult here to implement. So the reason this is a simpler solution, but we couldn't go with it because it was difficult to implement in terms of spurs. I take you back to this final solution. So we have PLL1, which is a narrowband fractional NPLL, followed by a post divider, kind of like that simplified drawing there. So I get a very good low phase noise reference around 300 megahertz or so fractionally controlled. And I pass it to what we call an integer and wideband PLL. So this is an LCPLL with a bandwidth of 10 to 20 megahertz, depending on the frequency of operation. Up to 20 megahertz bandwidth from LCPLL is a little bit challenging, and you have to take care of charge pump noise and what comes in the other path from a mixer and everything. And then the loop filter also matters here. Then in the feedback path of this PLL, as I explained, we have the BAW oscillator, down converting mixer, low pass filter, all of that. But if I leave it like this, it's still the BAW frequency. If it drifts, it changes the output frequency slowly. So we have a digital loop going around the whole thing. It's not much, you know, I only need to frequency lock this. So I have a sample of this frequency, and I have the MMD, and I have a digital loop fiddling with this fractional synthesizer that feeds into the reference of the second PLL. So this whole loop basically sort of looks like a monster, but it works very well. PLL1, narrowband, PLL2, integer and wideband, and PLL3 is just a digital loop to keep everything frequency locked. This is, I guess, putting everything together. This is phase, like a real spectral phase noise analysis of this system. Just focusing on the for this tutorial, the single slide just focuses on the phase noise components in the second PLL. So this is the whole output, but it consists of many underlying components. The main components contributing to the output phase noise is the reference clock 2 coming from the first PLL into the second PLL. So this is the main contributor. You see it here in yellow, reference 2. And in this table, I'm listing that the target spec here was minus 143 dVc per hertz at 800K offset. This is the one that translates to 200 something dB normalized form. But this is the actual dVc per hertz on on phase noise analyzer at 800 kilohertz. I'll show you the measurements next. This is the simulation at design time. And this typically we hit 144.5, and worst case is 143 almost. And the underlying components are these. So the main contributor is ref clock coming from the first PLL. At high frequency, you see a little bit of VCO of the second PLL coming into the picture. This is around the bandwidth of 20 megahertz, which is the bandwidth of second PLL I mentioned. Below that, remember the VCO noise gets attenuated, right? So it's not actually in the list of contributors in band of the second PLL, but above 20 megahertz, we have a little bit of contribution from VCO2. And then you have the post divider, like above the, when everything is said and done, you know, you have this post divider still sitting here. So that sets your noise floor. And then all the other components, PFD chart. So these are all within the second PLL. Everything from the first PLL is summarized into this ref2, which is coming to the second PLL. The bandwidth of first PLL is actually around 100 kilohertz or lower. I'll show you that in the measurement slide next. The contribution of the BAW is much lower, maybe 8-9 dB lower than the reference 2, and then down converting mixer and post divider. PFD charge pump, I guess, is still important. It's secondary after the reference clock 2. So everything here is combined here, gives you this red solid line, which is the output of the PLL, output of the second PLL. So these are the actual measurements. So this region is what we showed in simulation. So the noise floor bandwidth of 10 to 20 megahertz and the ref clock coming from the first PLL to the second PLL. So this hump is the wideband PLL. This hump around 60 kilohertz to, definitely below 100 kilohertz. This is the bandwidth of the first PLL, we call it narrowband PLL. And then the digital loop also has its own bandwidth, which is very low. It's in this case, it's around 1 kilohertz. It's programmable up to, well, in this case, it looks like it's below 1 kilohertz, but it's programmable up to a few kilohertz, from a few hundred hertz up to a few kilohertz. So we measure this LO at many different frequencies. Here in this picture, phase noise picture, I'm showing 3 final output frequencies, 1.7 gig, 1.5 gig, and 1 gig, right? 3 different phase noise profiles. And then for the radio chip, we need to sweep it across like many bands from 840 kilohertz up to 1.8 gigahertz. So this is the 800, this is just one cross section of all measurements at 800 kilohertz, right? Focus on this for all the possible radio frequencies, carrier frequencies. And as we see, they're all below the targets, 143 worst case or 144.8 or something typical. And this is equivalent to form of 212 gigahertz. So we arrived at a solution which is very high performance. It's based on BAW and it's tunable from 840 meg up to 1.8 gigahertz. And the integrated phase noise here in the order of 100 femtosecond RMS, again from 12 kilohertz to 20 megahertz. So this is from one of these curves, I guess. I guess this example, but this table and the integrated number is for 1.76, which is the green curve here. So the summary of this chapter, which is probably we're getting to the end of presentation, is, again, I don't want you to go through all the details of the evolution, but these bullets are kind of important ones. In the SerDes PLL or RJ RMS integrated jitter plateau to 250 femtosecond RMS, but those were more like classic low power fractional MPLLs with low voltage and single core LCVCOs. In our RF PLLs, we used high voltage swing LCVCOs. We use ultra thick metal inductors. So this is a little bit of cost adder that we get in RF process, deep envelope and everything in RF process. And we reached something in the order of 150 to 200 femtosecond RMS or a form of 200 dB with a single VCO. With a 4-core VCO. Sorry, is there a question?
No, I think.
Okay, so a single VCO, high performance VCO, high voltage, ultra thick metal gave us this 150 to 200 femtoseconds. So we pushed this envelope from 250 down to maybe 150 femtosecond RMS. Then we implemented a 4-core VCO and we reached the neighborhood of 100 to 120 femtosecond RMS or a form of 205 dB, a little bit of tuning because it's a LCVCO, but power was high and we still wanted higher performance. So we went to this LO solution with BAW in package, which got us to 70 to 100 femtosecond RMS and 212 dB form, which was the level of performance we wanted for that radio chip. And if you're interested in on a single low frequency or two, you can just use the low power non-tunable version of this for PLL. If you want tunability, you have to use more tricks. In this case, the mixer solution, and we made it tunable, and it comes at, of course, higher power and complexity. So how much time do we have? Should I go through the smaller chapters or just to future roadmap?
Yeah, I think we're 10 minutes over, but maybe you want to cover the last one, like future clocking roadmap. Maybe that'll help. I guess we'll wrap it up with that.
Okay. Okay. Yeah, so maybe as I just flip pages, I tell you what I was gonna talk about, but I don't have time to. So this is the jitter.
There's a quick one question, Hermos, if you allow.
Yes. Yes.
Hello.
Hello. Please go ahead.
Yeah, so my question is from chapter 2, multimode wideband VCO.
Chapter 2. Okay. Sorry, let me take you there.
Yeah, multimode wideband VCO.
I got it. Okay.
Yeah, so that
this one, for example.
Yeah, this one exactly. So that H-shaped thing, that's your inductor, right?
Yes. But you know, H could be a full loop, or it could be a two loop here, two loop here. But
yeah, and you have
this drawing shows the pattern, and actually the implementation. I wish I had the micrograph of the chip. It actually looks like H with some thinner inductor that thinner metal connections that takes you to the GM stage of the VCU.
Yeah, so my question is, how are you changing the coupling coefficient? That is what you did here, right?
Yeah, the coupling coefficient changes because of the polarity of the loops. So
as in the current flowing through the inductors?
Yes. So we force opposite polar. So if these mode selection cross-coupled drivers are off, and you turn on the system, the natural frequency, if with two inductors, you get A and B in phase, and that's one mode of operation. But when you have a cross-coupled, it always forces like a differential entity, right? It forces opposite polarity, and it's easy for this system to latch to that mode of operation too. You just need to force it. In fact, we can turn off these dividers, or these dividers, this cross-coupled driver is not very strong. We can turn it off, or we can keep it on. We can make it stronger. So there are many combinations here you can achieve in terms of performance and power. But the basic idea is whether or not to force opposite polarities here. Because when you force opposite polarity, you get I guess in this example, you get this loop and this loop sort of opposing, right?
Yeah.
And you can have the additive. So if the field adds up, in the effective inductance is the magnetic field divided by current. So the effective inductance changes in this system depending on the polarity.
Yeah, so are you familiar with on-chip transformer-based VCOs? This is similar to that, isn't it?
Yeah, there are many varieties of transformers are, they're, we don't have like a transformer per se here, but yeah.
I mean, you have two inductors with a coupling coefficient, so That's why I'm asking. So
yeah, and in this case, they are, but actually, electrically, we need to share a connection. So this is also sharing the connection.
Yeah.
Otherwise, things go wrong. And I mean, if I totally separate these two loops, it's something else. These are sharing one side, and in fact, you can maybe even overlap a little bit more or less, but and that's how you change the coupling coefficient. So you can get these curves spread out or closer, depending on how you design the coupling coefficient.
okay, thank you.
You're welcome.
Almost you want to wrap it up with the future roadmap?
Okay. Yeah, I
Yeah, I
guess
think we lost more than half the crowd here. Yeah.
Oh, really? Okay.
A lot of them have some transport arrangements. So.
Oh, okay. So there was the JATS chapter, and then there was the digital PLL chapter that we skipped. Again, we track form of digital PLLs, and this was for digital core and timing where period jitter matters. So future roadmap, I guess it's the roadmap of the whole group, but it also applies to clocking. So in terms of technology, we have large SoC products that integrate hundreds of millions of gates and use the latest CMOS technology nodes to deliver the best performance, power, and area, and rich feature set. In fact, I had examples of earlier chips in 40 nanometer in one of the slides that I didn't show that have 400 million gate complexity. It's more than 1 billion transistors. So these are like really complex chips. And then now in these deep sub 10 nanometer nodes, we are getting to more than billion gate complexity. So we keep going to deeper and deeper nodes, and we need to design analog in the same. So this is because of the digital. We are going to the 6 nanometer and 3 nanometer nodes, and we need to move along with the technology node. And at the same time, we go to higher rates, and we support higher rate standards with more demanding jitter. So we are designing a 6 nanometer in 2023. This year, we start 3 nanometer implementation. The hybrid and digital PLLs forms are improved in each technology node and clocking generations, so 15 generations. So here we're going to the 16th and 17th generation, right? So that we are going to design a 3 nanometer hybrid LCCSU for PCIe 6, which is 64 gigabit per second, and PCIe 7, which is 128 gigabit per second PAM4. Target jitter specs are 100 femtosecond RMS. Jitter filter is defined by the standard, and the target frequency, depending on standard, maybe 12 gigahertz, up to 32 gigahertz. So I'm basically saying what designs we have ahead. And for digital PLLs, again, designing in the same nodes for target frequency of 3 gigahertz or so. We need lower power supply sensitivity by co-designing PLL VCOs with LDOs and still maintaining the form performance. We explore new architectures, and we always track these standards. So there's the standards from OIF. They're called CEI, Common Electrical Interface. The latest published one is for 112 gig, and the one that's in development is for 224 gig. Equivalent of these in Ethernet world from IEEE are 100 gig per lane, which is actually 106 gig PAM4. And then the next one is 200 gig in development. 100 gig is already published. And from PCI Express, we're going to have the 7th generation. The standard is just started. It takes year and a half to 2 years to get to final standard, but the target is 128 gig PAM4. So we're going to design for these standards. We also have the automotive ASA, which is Automotive SerDes Alliance. We're going to design for these kind of specs wideband fractional length synthesizers, right? Because with wideband, we can attenuate the in-band phase noise, but then what do we do with the deterministic jitter of the fractional PLL? So we need some kind of error cancellation for the DSM, and there are newer clocking architectures that we're going to explore. In literature, you find a lot of injection locked oscillators, right, and multiplying injection lock oscillators. There's a new trend to go to subsampling PLLs. So these are the new architectures that we're exploring. More likely, more work will be done on subsampling PLL and also wideband fractional synthesizer, because we need to improve the RJ and still not suffer from the fractional noise. And then there's talk about on-die SerDes. This is actually in feasibility. Everything we talked about regarding SerDes is between two chips, right? But there are applications where inside a large die, we have pretty large dies, and in the order of 25 millimeter by 25 millimeter or so. So just to move clocks and data across those die, people are talking about now on-die SerDes. So this is one area that we can explore. And then there's chiplet applications, and everything involves clocking and clocking challenges. So in chiplets, there's SerDes and then digital core dies. They are implemented on a MCM or system in package, and they are communicating, the different chiplets are communicating using standardized interfaces. Two known standards so far for communicating between a core die and IO die. This IO is basically our SerDes, and the core is the core of the digital chip, which may be in the most advanced technology node. This may be in 3 nanometer, but we have chiplets coming maybe from 16 nanometer or from 6 nanometer that we want to keep, right? So through these standards, the chiplets can communicate to the digital core. One simple standard is literally called bunch of wires, BOW, and it's from OCP Open Compute projects. There's another chiplet standard, which is UCIe. This is perhaps more prescriptive. It's driven by Intel and a few other companies. UCIe stands for Universal Chiplet Interconnect Interface Express. And somewhat reminds me of PCIe, which was coming from Intel again. So basically, these are kind of products that a few years down the road we will have, and they all involve clocking and SerDes design. So I think I'm going to stop on that happy note.
I think good luck, Harmos, for your future and
thank you.
Stuff. Thanks. Okay. We have trouble. I think it's already 6:30 a.m., right? I believe there, Harmos. I think thanks for staying up so late.
This is 3:30 a.m.
3:30 a.m. Okay. Yeah. I don't think we can ask anything more beyond that to you. Okay.
No.
I think
that's
from
fine.
all of us,
okay, if there's question or anything, I guess, or where is the quiz or trivia questions from Satish?
You're not allowed to answer, okay?
Probably a wide round of applause for Harmos.
Yeah, well, what's the difference between period jitter and periodic jitter?
Yeah, thank you so much, Armos. I think a lot of the folks in the room definitely appreciate the fact that you stayed up late and still made this work, right? So truly inspired by your commitment, and thank you so much. Yeah.
No problem. I tried to.
So
turn
just
on my
we'll
camera
take maybe
later on.
1 or 2 questions in the benefit of his sleep versus your travel, all that. Maybe any last minute questions, short ones, or you can always connect with us and happy to answer on email as well.
Yeah, and we have experts in the room. Shiva, Sid, Satish, they can also answer. Like if you come up with questions later, I guess you can find them in the conference or keep in touch with me.
So I think the last time we did one session in, I think 2019 edition, Hormos had thousands of LinkedIn invites. So maybe you can prepare for it now, Hormos.
I wish we had some more time.
Okay. It's my pleasure. Okay. And hopefully
I have one
I'll
question.
get my visa and I'll travel
you told.
later in the day. Yeah.
There's one question in the room.
Yeah,
Okay.
you're telling, right, PCIe, instead of PCIe, we can use CXL. Is there any further SerDes 5? You're telling, right, in 2 years, you're going to, it is 120, PCIe 7 is 128 Gbps. Instead of that, is there any alternative, like PCIe is the advanced version of, PCIe advanced version is CXL, right? Instead of that, we can use CXL.
Yes, CXL protocol is based on PCIe. Yeah, so I imagine when PCIe 7 standard comes in, it supports CXL 4.0 or whatever that is. You know, I'm more tracking PCIe and electrical specs, but CXL is entirely based on PCIe so far, and I expect it to continue to be the same in future. Yeah.
Okay, thanks.
Thanks.
Okay, one last one. Anyone? Or is still people waiting for some quiz?
Yeah, go ahead, Satish.
I think in the future it might be. Yeah.
It'll take some time, but eventually it will be available.
Not today.
I have some housekeeping information. I'll share it after 5 minutes. Okay. After the quiz, I'll share.
Okay. Is that okay?
We'll take short quiz
3
followed by vote
seconds,
of
yeah,
thanks,
just-
and then some info about the delegation kits.
Okay, very easy one. Okay, to start with, I want people to go finish that. Right? How does a PLL loop filter jitter transfer function look like? I think there were 3 different options, right? Again, the same procedure, hands up and get the mic and answer, your name and answer. Maybe the first lady in the room.
Is it the PLL with a single core?
Yeah. PLL loop filter. Get the mic.
Yeah, it looks like a band pass filter.
Okay, that's is that right, wrong? What does others think? Right? Sure. Anybody else saying band pass? Okay, he's right. Okay. Okay, I think one of the slides he showed when the technology scale from different versions, right? I guess from 28 to 16, the FOM, the figure of merit, did not scale, right? Did you guys remember few reasons? Pick up the mic. Hands up and same rules. Your name first.
I'm Khader from Marvel.
Okay.
MOS cap density is one of the parameters which did not scale. I think the coil.
Yeah, the inductor size. Yeah.
Yes. Yeah, that's what I
think that's enough. Yeah. Okay. Okay, this is again an easy one. Okay. What does BAW oscillator stand for? BAW. Can somebody expand?
No, firstly. You're not able to.
Okay, he gets it. Any more left? Shiva? Or you are still finish off?
Yes, he has answered last time.
Okay, I mean, we'll go easy. So there were a lot of categories of clocking that he has listed, right? So can somebody remind what all types he has classified it as? Like clock IPs. Like he did some 4 different. The clocking circuits are categorized as different types, right? Okay, go for it.
This is Tanya. It's a digital, then the narrow band PLL, the wide band PLL, and all
Okay.
PLL, or AD PLL, all digital PLL.
Okay, you're going a little deeper, but at the top level, like at the macro level. Yeah, right.
Yeah, Sriharsha from Marvel. So pure analog PLLs, and he replaced some portion with the digital and tried to separate it, and RF PLLs where mixers are added.
Yeah,
that's
so basically SerDes PLLs, RF PLLs, digital attenuators, clock, CSU, like digital clocking basically.
DLLs also.
Okay, both gets half and half. Okay, you don't have to split it, but yeah.
Can I ask a question?
Okay, yeah, go for it, Harmus. Yeah.
What's the difference between period jitter and periodic jitter?
Okay, that's a good one to get people. Let's see.
Or is it the same?
Do you want to repeat the question?
Is there any difference between period jitter and periodic jitter?
Any jitter versus periodic. Any difference between period jitter and periodic jitter? Okay, there's one hand I can see at the back first. And if it doesn't answer, you will get it, okay?
I'm taking a guess. So period jitter is the jitter that you get within a period, and periodic jitter is, if you look at the frequency spectrum, then maybe the jitter that appears periodically. So I'm taking a wild guess.
Okay, there's one
Can
more
you
attempt here.
Okay, somebody, it's I think more
so-
than half the answer. Somebody else.
Yeah, someone else is trying. Let's see.
So period jitter can occur over a wide range of frequencies, but whereas periodic jitter occurs and it's concentrated at a single frequency.
Okay, so
One more
you're-
person. Let's try.
Okay.
One more attempt.
So period jitter, I think it's mostly based on a single, taking a single edge, like how much the movement happens, right? Like, but a periodic jitter, we take a lot of samples and try to impose the sine waves and try to see how much the width of like, it's mostly like an eye diagram. We try to analyze to see how the periodic jitter will comply to the whatever the IP which you are planning, right? Like the data rates and all. It's kind of important metric. Periodic jitter can play. That's what I think.
Okay,
I think
one more
last
attempt here.
One last attempt.
So if we plot jitter versus cycle, right? And if there is a pattern found in that, so that is probably the periodic jitter. You know, the jitter is following itself after a certain period of time, but period jitter is something, you know, which is deviation from the period of the clock itself.
Yeah, this like I guess all of you had a little bit of explanation. I guess the first answer was correct about period jitter. Second answer was more accurate on periodic jitter. Yours is probably a little bit better, most complete, I would say. I don't know how many prizes we have left, but probably the last answer is the best one, I would say.
Okay.
But everybody else also had partial answers.
You have one more, Hermos? I'll finish it with your question at the end.
Question we need to give to these guys.
So I should ask the question.
Yeah, if you have any, you can.
So how does the mixer phase noise differ from so when I change the frequency of the carrier using a PLL multiplier and divider, actually maybe we'll just keep the question to that. How does the phase noise change? So I have a multiply by N PLL followed by a divide by M divider. How does my input to ref clock phase noise change going through this two components?
I guess it is sums up the phase noise. You are trying to differentiate between the multiplier and the mixer.
Okay, no, I
multiplier,
took it back. No, I'm not asking about the mixer, I guess. Just the
multiplier shifts up the phase noise.
Okay, by how much?
Mixer sums up the phase noise.
Okay, multiplier shifts up by how much?
20 log n, yeah, okay.
20 log n looks like.
Yeah. And mixer, if one input sums up the inputs, if one input is ideal, then what's the output phase noise?
Input phase noise.
Okay, yeah. So even though it shows up at a different frequency, but it's still the same dBc per hertz. So that's, yeah, so you got, I guess, both.
We have vending machine full of chocolates if you want. We have vending machine full of chocolates.
Okay, so one even more a simple one. So you have the host here. Would anybody know his name? His name was the one that flashed from the time you came into the room. You should know by now. If anybody gets it wrong, they are going to sponsor something back, okay?
Except from Silicon Labs.
Yeah, you are not supposed to be from Silicon Labs if you're answering, okay? Okay, you're not from?
I'm Swami from MVSR Engineering College. His
Okay.
name is Rahmatullah.
Okay. There's one more name. Do you remember?
Sir?
There's first name, last name.
I know only one name.
That's enough. Yeah, that's good. Yeah, at least you paid attention in the room, right? So that's good. Yeah. Okay. And it's very, very rare to see the female engineers, and big claps to a lot of you guys showing up here.
I think thanks for all your patience, probably. Yes. I know it's a Sunday. Rashikar, you're saying something? You're saying something, Rashikar? Okay.
So maybe he's worried he's missing out on the chocolates. So.
Okay, thanks for all your patience. I know it's a Sunday, but I think we all had a meaningful Sunday. So I hope we're gonna design good band gaps and good clocking circuits going forward. Okay, wherever you go for work. I'd like to request Anil to come over here and present a memento to Hermos. I'll ask Satish to take on behalf of Hermos. So Anil is our RFI MS manager here in Silicon Labs. Thanks. I request Anil to speak a word.
Firstly, thanks, Hermos, for staying up late and having to continuously talk to close to 3 hours. Really appreciate the session. It was very insightful, covering from the basics to very advanced topics in a very clean and simple way. Thank you, and it was very, very insightful. At least it was. I think at least I've learned a lot in this session. I hope the audience also felt the same way. And thank you, audience, for being very, very proactive in asking questions, being very engaging, and throughout both the sessions. I was not in the first session, I came only for the second session, but in any case, I like the spirit. And thanks also for the Silicon Labs management for being part of the conference and being one of the gold sponsors. So, and thank you, Ramtala, for hosting the session.
Thanks, Anil, for your kind words. So I thank all again, IT admin for facilities, our security, all the staff who has helped in hosting all this session. Okay, those who has registered as the fellows or who are outside of Hyderabad, right? There is something called delegate kit. You can collect it from ground floor lobby. If you are a Hyderabadian or you are not registered as a fellow, right? You'll get it at HICC. Okay, the delegate kit you'll get at HICC on the last day of the event. Clear, right? If you have registered as fellow or if you are not from Hyderabad, you can collect it at ground floor lobby now. Okay. Thanks all. Please use this third floor lift for getting into ground floor.
Hey, thanks everyone. You have
Thanks,
been
everyone.
a real
Thanks, everyone.
sportive
Thanks,
audience,
everyone.
and
thanks, Hermos.
have
Who
a
are online.
good day and rest of the conference as well.
Bye.
Thanks, Hermos. Good night.
Thank you very
Bye.
much.
Thank you, Hermos.
Thank you, everyone. Thank you.
Have at least some sleep.
Yes.
Okay, good night.
Thanks, everyone. Bye.
As a fellow. Okay.